Hi, I am so glad you guys made it to this segment, Math Tips for the Frustrated Algebra Student. Is this you? Do you get to your tests and all of a sudden you go blank? Maybe you've done all the homework and all the homework made sense, but the test, you just don't recognize anything. Or perhaps you understood stuff in class, but when you got home to do your homework, it doesn't look anything like you did in class. It looks like Greek. Or worse yet, you're actually in class and your teacher does not make sense. So you feel like giving up. Did any of that sound familiar to you, or perhaps all of it sounded familiar to you? I want you to take a close look at this segment. We're going to talk about how to take notes, how to do your homework, and also how to study. A lot of students don't know how to study for a math test, so we'll cover that. But first of all, I want to ask you something. What do you think is the most popular algebra question? The most popular question that all algebra teachers hear? Nope, it's not reading problems, it's not about factoring. When will I ever use this? That is the most popular question, and it's annoying, just so you know. But here's one thing I want you to understand. A lot of the math, you may not use it. Yeah, surprising, right? You think as a math teacher I'd go, oh, it's all important. It is. There's some stuff that you will use. There's some stuff that I use all the time and I don't even realize that I'm using it when I'm budgeting, when I'm doing my finances. But unless you're going to be an engineer or a computer scientist or a writer for some, geeky sci-fi, forensic show, which I love, by the way, fandom. Oh, okay. You probably aren't going to use all the math that you're learning in some of these algebra classes. So here's the next question. Why are we required to learn it? If it's not so much about the math itself, then what is it about? It's to strengthen the critical thinking part of our brain. Did you realize when you're learning math, it actually uses different parts of your brain? Let's take a look at this picture here. Here's a picture of the brain. Isn't it pretty? And all of its different segments, and all the segments are responsible for different duties. Here in the green is the temporal lobe. It's responsible for not only language, but as far as math is concerned, memory and learning. So learning 1 + 1 = 2, or the definition of an absolute value, that's going to use this part of the brain. However, do you see the big red part right there behind your forehead? That's called the frontal lobe. Now, it's responsible for consciousness and controlled behavior, but it also is responsible for problem solving, decision making. It regulates these sort of things, and this is where you use algebra. And this is why a lot of people struggle with it, is you're not using just one part of your brain. You're using two parts of your brain. And the algebra part is the part that we are trying to strengthen. When you get out in real life, we need you to be able to problem solve. We need you to make decisions without getting nervous. Now, one thing I want you to notice, both parts of the brain also regulate emotion. They're the only two parts that do that. So the two parts where you're learning math are also the two parts that regulate emotion. That's why some of you get a stress headache. You got two places here that's like working really hard, but also you get frustrated and you get anxious. You may do all of your homework just fine and you get to the test and you go blank and you start to sweat and you start to get frustrated and your heart starts beating. It's normal. So let's get you past that part. Remember, it's, don't give that excuse of, I'm never going to use this. Why do I have to learn this? It's so you can strengthen this part of your brain. So think of an algebra problem like a life problem, okay? Here you are, you're given some equation and you're asked to solve it. Here's your goal. You want x equals a number. So you need to figure out what tools do I have algebraically that's going to get me from my equation to my solution. It's the same thing with life. Here you are here, you're a couple, you're about to have a baby, oh, how exciting, and then one of you loses your job. You still have your bills, you still have to buy a crib. What are you going to do? What tools do I have to get from here to here? Okay, where else can I apply? I can set up my resume. Maybe I have family and friends who can help. I can call my creditors and ask if they can defer my payments for a while until I get past this slump. Maybe I can do a modification loan on our house. We can go and borrow. Yeah, all these things that you can do, but don't panic. That's this part of the brain, okay? So that's your goal in learning all of this. You are strengthening this part of the brain. So if you get a headache when you're learning math, you're doing it right, just like working out a muscle. So now let's take a look at taking notes. First of all, write everything down. Even if it makes sense, what your teacher's saying, write it down and add your own notes. Some teachers, they give lots of examples, which is fine. It really works for some students, but some students need a little bit more. So if you're not sure how they got from step A to step B, write a little note to yourself and, explain it to yourself why you're doing what you're doing. Also, sometimes your teacher might go a little fast if they're running out of time. So don't feel like, oh, you're behind, I don't get it. Just put a question mark and keep going. If you sit there and try to figure out, okay, now wait, how did they get here? I don't understand this step, and they're 3 boards down now, and you're behind. So write a quick question mark where you got lost, and then pick up after that. Also, go over your notes immediately, as soon as you can, and make any corrections. Because sometimes, it makes sense while you're writing it, but you're listening, you're watching, you're writing, and sometimes you might miss something. So as soon as you can, go over your notes and go, oh, wait a minute, that's incomplete. I remember what they said. Or go ask your teacher or a friend and say, I'm missing something here. This doesn't make sense to me. And then you can correct it immediately. Also, for some of you, using color can be very helpful. I mean, imagine a blank sheet of paper with nothing but, black print on it. And then all of a sudden, there's a word in red. Okay, guess where your eyes are going to go? In red. And guess what page your eyes are going to remember? Red. So give your brain more senses to think of it. If it's a quadratic equation, circle it in red and maybe put parentheses in red to think to factor or something like that. Now let's take a look at some of the homework notes. First of all, give yourself white space and margin in your homework. Imagine reading a book that's just side to side, top to bottom, nothing but words. Your brain will explode, right? Your eyes and your brain needs white space in order to absorb the information. Do the same thing in your notes. I appreciate the fact that you want to save paper. Buy recycled paper. Money's made out of paper, and having to take a class again takes up a lot of resources, which you don't want to waste as well. So use a little bit more paper, give yourself some room and some white space. Also, don't procrastinate. If you're given homework on Thursday that's due Tuesday, don't wait till Monday night to do it. You've probably forgotten stuff. You're going to look back at your notes and it may not be as clear and as quick. Do a little bit every day if you can, and that way you don't forget. Also, check your answers and ask for help. A lot of teachers, they grade homework based on trying it. Did you try it? Was it complete? Was it neat? Neatness and completeness, which is awesome. Hey, I got 5 points. I got my homework. Yay. You can get full credit for all of your homework and still fail the tests and then fail the class. If you're practicing it wrong, it's a waste of your time. So check your answers. Be sure you're doing it correctly. Also, make a connection between your instructions and your problem. This is huge. Highlight this one. This is for those of you who say, I can do my homework just fine, but I get to the test and I freeze. When you're doing your homework, odds are you're doing it in one section and you're doing 20 problems that are all alike. This section, I have to factor every problem. This section, I'm solving a linear equation. Great. And you do it, and you do it, and you do it. You're in a routine. When you get to the test and it's over 3 chapters and all of these problems are mixed in together, you need to be able to figure out, okay, wait, how is this problem different from this problem? And this is your key. Look at what are they asking me to do? Solve, okay? When I solve, I'm looking for my variable. My variable equals a number, okay? I need to whittle this down to get to that. How do I do that? What's in my way? That's where you make the connection. And if you do that while you're doing your homework and you actually talk yourself through it, physically, out loud, say, okay, I'm sorry. Don't do it in a public place. You might get sent away somewhere. But if you're home, talk to yourself and say, how do I get from here to here? Why did I subtract here? Why did I divide here? Why did I multiply here? Why did I move this here? What's my goal? If you can talk yourself through it while you're doing your homework and explain it to yourself or someone else, that's why working in groups is great, then when you get to the test and you get nervous, you can go, okay, wait, it's in here. What am I being asked to do? What does my result look like? How do I get from here to here? Okay? So be sure that you make that connection between the instructions and the problem. And last but not least, 5 and 4 kind of related. Ask yourself, what is my goal? What is in my way? How is this different from the other problems? If you can answer those questions while doing your homework, then when you're on the test, it's the same questions. Okay, so don't forget, give yourself white space, don't procrastinate, check your answers and get help if you don't understand them. Make a connection between your instructions and problem and ask yourself some questions. So here are some techniques now for studying math. These are my favorite. First of all, spot check your homework. If you know your test is going to be over 2 chapters, then take all of those sections of homework and literally spot check it. Close your eyes, go to the first page, this one. Okay, could I do that? And you don't even have to rewrite it. Spot check it first and go, okay, my instructions were this, I was asked to do that. Okay, I remember doing that. Okay, second section, this one. Oh, wow. Oh, I've forgotten about this. What did I do here? Oh, that's right. And then you kind of know where do you need to spend a little bit more time. What do you know and what do you don't? Spot check. Doesn't take long. Then outguess your teacher. This is always a fun game. What do I think my teacher would put on the test? And then go through your homework and pick maybe 3 or 4 problems from each section that you think your teacher would ask. You know, easy ones, hard ones, be sure there are reading problems involved. Don't just stick to the stuff that you know. Try some of the more difficult ones as well. Also, make a cheat sheet. Now, before you get too excited, notice cheat is in quotes, and you're not supposed to use it on the test unless your teacher says you can. The question is, if you were allowed a note card on a test, what would you put on it? Okay, what would you want on it? Then make it out and study that. Oh, I wish we could have a note card. Then I could put all these formulas on it. Okay, make a note card with the formulas on it and study it. Put them on note cards. Think about them. Memorize them. You know, carry them around with you. If it's, how to solve a problem, put it on a note card. The more you write it, the more you see it, the more likely your brain will access it when you're nervous. Also, teach someone else. I know this is an old adage, but you really don't learn something until you teach it. So get into study groups, explain problems to other people, explain them to your friends, to your parents, your roommates, wherever you are. Find somebody, explain it to them, and then it will stick a little bit better. And this is huge. Do not wait. Don't wait to ask questions. I've had so many students turn in their exam. Several of the questions are blank. And then they wrote me a little note saying, I never really got section 2.3. Why are you telling me that now? Okay, I'm going to cry. It's like, why did you wait till now? I'm not scary. Some teachers are, I get it, find somebody else. But most of your teachers, they're not scary. They want to answer your questions. And if asking in front of a class makes you nervous, find a tutor. Find another math teacher that will answer your questions maybe after school. But find somebody. There are a lot of resources out there. But don't wait until test time to admit you didn't get something. Don't let your pride keep you from passing. You can do this. If it takes you a little longer than somebody else, who cares? Okay? I was always the last one to turn in my test. Do you think anybody remembers that? No, just me. Nobody else cared. Don't worry about everybody else. This is not a competition. The most lonely feeling is everybody in here gets it but me, and I guarantee you that is not the case. I've got students, oh my gosh. Okay, little side note in here. I have students sitting on the front row, and I can just tell who they are because they're sitting there going, oh, and they've got this light bulb understanding look on their face, and they're writing notes, and you know what they're thinking? I have no idea what you're doing. I'm so lost. Oh, yes, I'm going to drop this class as soon as I can. Okay, so just because they're not asking questions doesn't mean that they get it. So be brave, believe in yourself, and realize it's okay not to know everything. It's okay to not have it mastered yet. That's what the test is for. If the test isn't here yet, you've got time. But don't wait, and be sure and ask questions. Okay, I'm off my soapbox. Next, study tips. So those were some techniques, but here are some things that will help. Water. You have to be hydrated, not only while you're learning the material, but in order to access the material. I know a lot of you, soda, coffee, you're going, I need my caffeine, I need to stay awake. They're great, but they dehydrate you. Drink it after, okay? Be sure you have it afterwards. Or drink it before, but also drink water. Water keeps you hydrated, and that's what your brain needs to make those connections. So if you want to access information that's there, water. Also, research has shown that peppermint helps. Gum, but I know a lot of places don't let you have gum, but chewing the gum, but more importantly, the fact that it's peppermint, the smell, the taste, it opens up the synapses and helps you to recall information that's in your brain. Now, it has to be there to begin with. Hence, show up to class, take your notes, do your homework. But if it's there, Peppermint helps you access it. Now, the next three has to deal with your senses. Whenever you can, talk out loud. When you're doing your homework, when you're studying something, say it out loud, let your ears hear it, write it down. If you've got a formula, like later on, or maybe now if you're learning it, the quadratic formula, every time you have a problem that uses the quadratic formula, rewrite down the formula. You're saying it, then write it, and that gives you a touch sense, you feel it, and then read it. Visual. And some of you may want to lose color. The more senses you use, hear, touch, vision, you're going to be able to access it. The more your brain has a chance to access it, the more likely it is to do it when you're nervous, okay? So talk out loud, write it down, and read it. Last but not least, start early. Don't wait until the day before the test to start studying. Study a little bit every day. Spot check your homework as you go. And that way when you get to the end, you know what you need to review and look over, okay? And my last tip, breathe. You also need oxygen. Believe it or not, you need oxygen to study. Your brain needs to be hydrated and it needs air. It needs oxygen. Take a deep breath and just tell yourself, I've done my homework. I've corrected my homework. I know I did it right. I've taken notes. Therefore, I know the information is in here. All I have to do is calm down long enough to allow myself to access that information. I can do this. Breathe. Okay? So, I know you can do this. Math is challenging. I'm not saying it's easy, but it's not impossible. Okay? It's a challenge. You can do it. And if you have questions, ask your friends, ask your teachers, ask your tutors, ask somebody. Don't let your pride keep you from passing. Okay? So we've got a lot more videos on factoring and solving equations and the like, so be sure to look us up, and hopefully we'll see you again soon. Hi. Today we're going to take a look at solving linear equations. And here's a polynomial equation that's linear. ax plus b equals c. A helpful thing is to be able to recognize the type of equation you have. It's not such a big deal now when you're first learning how to solve them, but later when you get closer to your final and you have all different types of equations together, it really comes in handy. So what makes an equation linear? Your highest exponent is 1. Polynomial equation, and you do not see any exponent with your variable. No x squared, no squared root, anything like that. So, one of the concepts that we have to focus on when solving any type of equation is we have to keep both sides of that equal sign equal, okay? So let's suppose we start with 3 equals 3. It's a true statement, but if we add 4 to only one side of the equal sign, it's no longer equal. We have 7 equals 3. So in order to keep it equal, we also have to add 4 to the right side. Then we get 7 equals 7. So even though we've changed the value on both sides, we've still maintained the integrity of the equal sign, okay? So it's still equal, still balanced. It also works for subtraction. If you subtract 5 from the left, we also have to subtract 5 from the right, therefore it stays equal. And it works for addition and subtraction, but also for multiplication and division. If we multiply both sides by 6, we get 12 equals 12. Divide both sides by 3, we get 4 equals 4. So as long as we maintain the inequality, we're safe. Now what skills do we need in order to solve linear equations? We have to be able to combine like terms, distribute, and know a little bit about inverse operations. Now, when we talk about operations, we're referring to addition, subtraction, multiplication, and division. But what makes them inverse? Technically, definition of inverse means that they reverse the effect of each other. But what does that mean to you and me? Basically, they undo each other. Think of addition and subtraction. They're paired up, they're opposites. Multiplication and division are paired up, they're opposites. So those are the two groups of inverse operations that undo each other that we're going to use when solving linear equations. Addition and subtraction, and multiplication and division. So, whenever you solve any equation, doesn't matter if it's linear, quadratic, or what, our goal is to get the variable by itself. We want to know, what does x equal? X equals some number and we need to find it. So suppose we have this original equation here. it's linear, polynomial, where your highest exponent is 1. And we want to figure out what does x equal. So we're going to manipulate that equation until we can whittle it down to just x, equal sign, and a number. So that's where I want you to think when you get to a test and you get really nervous. What's my goal? I'm going to solve it. I need to get x equals a number. So what's in my way? How do I get there? So right here we find the x. It's on the left-hand side. Now here's a 2 attached to it. So you've got an x term, but here we have a constant. So the first thing we want to do is to get the x term alone. So we're going to undo that subtraction, that little minus sign, by adding the 3 to both sides. So we add 3 here, there's your equal sign, add a 3 there, we get 2x equals -6. Same problem here, we've got the term by itself, but I still have a 2. So now I want to whittle it down a little bit more and get rid of this 2. So what's that operation in between the 2 and the x? Multiplication. And how do we undo multiplication? Division. Good. So to get the x alone, we're going to undo the multiplication using division. So if we divide both sides by 2, 2 divided by 2 is 1, which is what we wanted. 1x equals -3. Yay! Now, that was just kind of a basic, straightforward problem, but what if it gets really messy? Don't let those problems intimidate you. For example, let's suppose we have this guy. It's kind of long. I want you to remember that an equation is like 2 expressions set equal to each other. So we can just cover up the equal sign in the right-hand side and figure out how can we simplify this so it's not so ugly. Yeah, we can get rid of that parentheses by distributing. So let's go ahead and do that. If we distribute the 3, we end up with 6x minus 15 equals. And then we can focus just on the right-hand side separately, where we have 2 like terms here, the 2x and the minus x. If we combine those, we'll get a single x, and then we still have our plus 5. Awesome, so the sides are simplified, but remember our goal is to whittle it down to get x equals a number. How many x's do we have? 2, right? 1 on the left, 1 on the right. So we need to use addition and subtraction to move one of those x terms. So I'm getting rid of the x here, I'm going to subtract the x, but again we have to do it on the other side as well. That leaves us with the 5x, bring down your minus 15 equals 5. So as you're working it, be sure you're bringing down everything. This is 0, so that's why it's not showing up, the plus 5. And if you kind of focus on that, you're not going to miss anything. That's where the careless errors tend to come in. So now we're back to the other example. We have 1x, it's on the left, so let's get this term by itself by adding 15 to both sides. Let's move it up here so we have a little bit more room. And now we want to get the x by itself by moving that 5 using division. X equals 4. Now I want you to try. Here's 2 examples. Pause the video when you're ready. Try them on your own, and then we'll work them together here in a minute. Pause it. Yeah, pause it while I'm making this face. Okay, let's see how you did. The first equation, it's linear. You got a polynomial where the highest exponent is 1. And we need to get this x term by itself, so we're going to undo the addition of 5 by subtracting 5 from both sides. Now, for some of you, if you're having trouble reminding yourself that you have to do it to both sides of the equation, highlighting it would help, just to make sure that you see 2 every time that you create something on one side, that you're creating it on the other. A common mistake that we see here often is because this is a -3, they want to add 3 or divide by a +3. They're wanting to do the opposite of this sign. But remember, we're doing opposite operations. It's not 3 minus x or x minus 3. It's -3 times x. We're multiplying. So what undoes multiplication? Division. Good. We're whittling it down. So we're going to divide both sides by -3. And again, we can highlight. -3 divided by -3 is a +1, which is our goal. We want just the x by itself. And remember, negative divided by negative is a positive, so we're left with a +7/3. Your teacher may want you to change it to a mixed fraction, which is fine. 3 divides into 7 twice with a remainder of 1. So we're left with 2 1/3. Okay, let's take a look at the next one. This one is a little bit more messy, so we have to simplify both sides of the equation first. Here we have a 2x and a 3x that we can combine, okay? Two like terms here. That would give us a 5x, and then we still have that minus 5. And on the right-hand side, we've got this multiplication, so we can distribute and get rid of that parentheses, 2x minus 8. So now it's not as intimidating. You just took it one step at a time. If for some reason you get kind of overwhelmed by visualizing everything, keep a second piece of paper with you, a blank second piece of paper with you. Cover what you've already worked with, and then just focus on what's left, okay? So here, remember, we're trying to whittle it down to get x by itself, but now you have x on both sides of the equation here. So we've got to move one of them. I chose the 2x, but it doesn't matter which one. You can move the 5x, 2x, you'll get the same answer. So here, we're going to subtract 2x from both sides. Again, we can highlight to make sure that we've done it to both sides of the equation. Oops. So we'll be left with a negative 8 on the right-hand side, and on the left, that gives us a 3x minus 5. So now we're getting closer. Our x is, we see only one of them now. It's over there on the left. So let's get the constants together. Let's go ahead and move this 5, undo that subtraction using addition. And that leaves us with a 3x equals a negative 3. I'm going to move it over here just so we have a little bit more room. Okay, and now to get the x by itself, we're going to undo that multiplication by division, dividing both sides by 3. Oops, I was thinking of the other problem apparently. Dividing both sides by a positive 3, because it's this 3 that we're getting rid of, because 3 divided by 3 gives us a positive 1x, that's what we wanted. Negative 3 divided by 3 is a negative 1. There is one more example, so don't hang up on me yet. I know this wasn't on the slides that we were looking at, but I wanted to be sure and give you an example with fractions in it. I know fractions tend to just scare students a lot, but I don't want you to be afraid of them. Remember, fractions mean division. You know, this is 2 out of 3, but it also means 2 divided by 3, 1 divided by 2, the 2/3 and 1/2. What undoes division? Multiplication. So what you need to do to figure out how to undo that fraction is what undoes division, multiplication. So let's take a look at the least common denominator of our two fractions here. Least common denominator would be 6. Now, what would we do with that 6? We're going to multiply to undo the division part. So if we multiply the left-hand side, there's our 2/3 x minus 4 by 6, and the right-hand side by 6. Basically, we're going to distribute. So again, we've multiplied the left-hand side by 6, the right-hand side by 6. But over here on the left, we're going to distribute. Normally, most people only show this third line where they've distributed the 6. I'm going to put the 6 after the minus 4 so it doesn't get too confusing there with the minus sign. Doesn't really matter, but just in case. So notice everybody gets multiplied by the 6. I wanted to show this step so you know that we are technically doing it once on each side. We multiply the left-hand side by 6. We multiply the right-hand side by 6. But we did distribute. The reason we're doing this is every denominator divides into that LCD evenly. Therefore, we no longer have a denominator. For some of you, it might help to write those LCDs over 1 just as a visual, because some of you are still having trouble with your fractions. And that way you know that it's the 1 times the 3 and the 2 times the 6. So 3 divides into 6 twice. Now this denominator is 1, so we don't need to write it. Same thing here. 2 divides into 6 3 times, so now this denominator is 1, so we don't need to write it. All we do is now multiply across and simplify. So here we have 2 times 2x, which gives us 4x. 4 times 6 is 24, and 3 times 1, which is 3. It's a little bit nicer. You don't have the fractions anymore, and we can solve it like we did the other two examples. So if we add 24 to both sides, changed my method there. That's okay. That leaves us with a 4x equaling 27. And then 4x equaling 27. We're going to undo the multiplication between the 4 and the x by dividing both sides by 4. 4 divided by 4 is 1. That was our goal. So we're left with x equaling 27 fourths. That's an improper fraction. It's improper because the higher number is on top. Mixed fraction, we can divide. 4 goes into 24 6 times with a remainder of 3. So we get 6 3/4 as our mixed fraction. Ta-da! So how did you do? Double check and just kind of see, were your errors careless or were you really clueless? Do you need to watch the video again? And also remember, don't let your pride keep you from passing. Talk to your teacher, your friends, see more videos. There's plenty of resources out there, okay? So ask for help. A few things to remember. If you do not see any variable exponent in a polynomial equation, then it's linear. Your goal is to get the x by itself. You want to know what x equals, so you got to whittle it down. And then we're going to separate our variables from our constants to help us get our x alone by using inverse operations to undo each other, to get rid of those obstacles. Well, I've had fun. I don't know about you, but hopefully it was better than drinking your own bathwater. It wasn't too bad. And I'll see you next time for the next video. Hi, welcome to our first video on factoring. Today we're going to cover some factoring basics and the greatest common factor, affectionately known as the GCF. Now, some of the basics are true for all factoring, so it's not just about the greatest common factor. So go ahead and have these in your notes somewhere that you can refer to for later. The first one is factors are multiplied in order to equal a product. So it's important to understand what a factor is when you're asked to factor something. So if we have 2 times 3 equals 6, we have a factor times a factor equaling a product. In other words, 2 and 3 are factors of 6. Likewise, if you have 2 binomials being multiplied to give you this trinomial here, we still have a factor times a factor equaling a product. So a factor can take different forms. So basically, when you're asked to factor a trinomial like this, you're asked to put it into the 2 binomial factor forms. So factoring is taking a product and rewriting it as 2 or more factors. Now, we also always want to factor completely, meaning as much as possible. We don't want to just factor out one piece when other pieces can go a little bit further. Think of prime factorization when you do the prime factor tree and you keep going as far as you can. Same idea. Now, here are some hints. First of all, be sure your polynomial is in descending powers. In other words, have the highest exponent first. Say x squared, then your x, and then your constant is always last. 2, look for a GCF first, if any. In other words, it may not have a GCF, but we always want to look because that makes the rest of the problem a lot easier if we do have to go further. Also, if your first term is negative, I always like to factor out that negative. It just makes the rest of the polynomial easier to deal with, again, if we need to go further. So what do I need to know? What tools do we need in order to factor? First of all, we need to be fairly comfortable with our multiplication facts. Also, we need to know how to distribute, how to divide, and the FOIL method. I don't use the FOIL method a whole lot when multiplying, because you multiply them all the same. But that pattern of FOIL, when you multiply 2 binomials, is a huge helper when you're trying to factor into the two binomials. It's like undoing the pattern. So the FOIL method is something that's really handy to know. So let's focus on the greatest common factor. What is that? It's the largest number and or variables that are factors of every term in a polynomial. Okay? So let's look at this trinomial here. As our coefficients, we have 6, -12, and 9. So what's the largest number that would divide evenly into 6, 12, and 9? Good, 3. So 3 is going to be part of our GCF. And then we look at all the terms. They all have an x. There are 4 x's in the first one, 3 x's being multiplied in the second one, and 2 x's in the third one. So we want to know how many x's can we divide out from each term. We want as many as we can, but it has to be the same amount from all 3. We can take out 4 from the first one, but we can't take out 4 from the third one or the second one. So the most x's that we can divide out of all 3 would be 2. So every term is divisible by 3 and x squared. Therefore, our GCF is 3x squared. Now let's recall distributing. If we have the monomial 3x squared here being multiplied by this trinomial, we would distribute that 3x squared into every term by multiplication. So when we distribute to the first term, we would get 12x to the 5th. To the second term, -6x cubed. And the third term, -15x squared. The reason this is important is because you can consider factoring out the GCF like the distributive property backwards. Instead of starting with the parentheses and multiplying in, we're going to start with the trinomial or binomial, and we're going to factor out or divide out. So here we have 15x cubed minus 10x squared plus 35x. First, we need to find our greatest common factor. 15, 10, and 35. They're all divisible by 5, nothing larger. Also, all of them have an x. The last one has a single x, so that's going to be part of our GCF. Every term is divisible by 5 and x, so 5x is our GCF. Notice the GCF is on the outside of the parentheses, and now we're going to do the distributive property backwards. So we need to figure out 5x times what term would give us 15x cubed? Well, 5 times 3 and x times x squared, so we have 3x squared. 5x times what will give us a -10x squared? -2x. And last, 5x times what would give us 35x? Good, a +7. So that's our result. That's the distributive property backwards. You can imagine, what would I need to multiply it by to get this term? What would I need to multiply by to get this term? There's another way of looking at it. Factoring out a GCF is like dividing out the largest common factor. Well, we determined the GCF was 5x, so we're going to divide everybody by the 5x. So the 5x is still our GCF on the outside, and now we're going to factor it out by division. If we look at the first term, 15x cubed divided by 5x, that would give us 3x squared. The second term here, -10x squared divided by 5x, would give us a -2x. And then lastly, 35x divided by 5x would give us a +7. So we end up with the same answer that we got doing the distributive property backwards. It's the exact same idea, but some people find it handy actually dividing by the GCF so they can see what's left inside the parentheses. Okay, same result. Now, here's kind of a special example. We have a 24, a 4, and a 2 as far as the numerical coefficients here, and the largest number that divides in evenly in all of those is 2. But we don't have an x here in the last one. We have 2 in the first one, 1 in the second one, but we don't have an x in the third one. Therefore, our GCF is just the number 2. They do not all have an x in common. It's the greatest common factor. Also, when we divide out the 2, well, 24 is divisible by 2, we get 1. 4 divided by 2, we get 2. A lot of people look at, oh, 2 divided by 2, and they use the word cancel, and they get slash happy, and they think, oh, it cancels, meaning it disappears, and it's just gone. The problem is 2 divided by 2 doesn't disappear. 2 divided by 2 is 1. So be sure that you have that 1 showing up. And you can always distribute the 2 back in to make sure that you get your original. Also, here's another example, 3x squared plus 5x minus 9. Well, 3 and 9 have a common factor of 3, but the 5 doesn't. Okay, so remember, it's all or nothing. They all have the same factor, or there's no common factor. So there's no numerical common factor. Also, the first term has an x in it, the second term has an x in it, but the third term does not. Therefore, this example has no GCF, and that's okay. Sometimes there's a GCF, sometimes there's not. We may be able to factor it further in a different way, and we'll show other methods on the next videos. But right now, just the GCF, there's not one. So, here's some examples for you to try. Go ahead and pause the video, look for a GCF, factor it out, show what's left, and then go ahead and hit play when you've tried them and you want to see the results. Pause it. Go ahead and try it. Okay, let's see how we did. Remember, our instructions were to factor out the GCF. Here with 18 and 24, they're both divisible by 6. That's the highest number. The first term has 5 x's, the second one has 3 x's. We want to take out as many as possible, but it has to be the same amount of x's from each. So we can take out 3 x's from both. So our GCF is going to be a 6x cubed, and let's see what's left. 6x cubed times a 3x squared will give us the 18x to the 5th. 6x cubed times 4 will give us the negative 24, or times the negative 4, gives us the negative 24x cubed. And you can always distribute back in to double check and make sure you get your original back. Let's take a look at the second one. Here, the 8, the 12, and the 4, they're all divisible by 4, and they all have an x, so we can take out a 4x. And again, one of the methods, as opposed to just visualizing the distributive property backwards, is you can physically divide out each term there by your GCF, and that will help you determine what's left. So let's see what we've got. 8x cubed divided by 4x would leave us with a 2x squared. Negative 12x squared divided by 4x is a negative 3x. And here, 4x divided by 4x is 1. Don't get into the habit of just saying, oh, they cancel out, and you start getting slash happy, and it disappears. There is a term there. So this is your result. Now, I know I've circled it here because we're focusing on a GCF. Remember at the beginning when we started talking about factoring basics, I said you always want to factor as completely as possible. This trinomial here, can be factored into 2 binomials. So it can be factored further, and we're going to learn this later. So this is more to come. Okay, and we'll show you how to do this on the next video. But for right now, let's take a look at C, where we have 12x to the 4th plus 9x cubed plus 2x squared. The bummer here with the coefficients is that the 12 and 9 have a 3 in common. The 12 and the 2 have a 2 in common, but there's not a common factor among all 3. Therefore, we can't take out a number, but we can take out the variables. There's 4x's here, 3x's here, 2x's here. We want to take out as many as we can, but it has to be the same amount from each. So the most that we can take out is going to be the x squared, always the smallest. Okay, so we can take out the x squared and be left with 12x squared plus 9x plus 2, which this one cannot be factored further, so you would be finished here. So how did you do? Kind of double check yourself, see where your errors might have been. Did you forget, one of the terms inside? Did you take out a GCF that really wasn't a GCF? Once you determine where some of your errors are, then it's easy to correct them. Those are the things that you need to look out for. So, just to recap, to remember, always look for a GCF first. Not all polynomials will have a GCF. Factoring out a GCF is distributing backwards or dividing out the GCF. And we can always multiply back in to check. The only thing I warn about this is I've had a lot of students, they're asked to factor, so they factor it, and then they multiply back in to check it, but then they circle their check. Well, when you check it, that should be the same thing as your original problem. So be sure you circle the factoring part, then check it to make sure it matches the original problem, okay? So thanks for watching. Be sure and watch our other videos on grouping and factoring trinomials to get those two binomials that we're looking for and other special factors as well, okay? So thanks for watching. If you have any questions, watch the video again, look for other videos, ask your teacher, ask your tutors, ask your friends, but ask, okay? Don't let your pride keep you from passing. You're almost done. I can feel it. Have a good time, and we'll see you again soon. Hi. In this segment, we're going to look at factoring polynomial expressions using the grouping method. But first, let's review factoring out the GCF. Remember, if we had 24x squared plus 4x plus 2, you're looking for the largest number and variable that would divide evenly into each of these terms. Well, they don't all have an x, so they're not going to have a variable GCF, but they're all divisible by 2, and that's the largest. So we'd factor out a 2, and we'd be left with 12x squared plus 2x plus 1 in the parentheses. So let's imagine our GCF now being a binomial and not just a number or variable. In this piece here, it has an x plus 2. This piece here also has an x plus 2, and they're separated by this subtraction sign. So visualize factoring out an x plus 2 as your single GCF, just like we did with the 2 previously. Well, if we take out the x plus 2, then we are left with the 3x and the minus 7, and that's what creates our second binomial. We're going to use this in the grouping method here in a second. So, with grouping, we need to know when we have 4 terms, that's when we can use this method. You always look for a GCF no matter how many terms you have, then you start counting the terms. If you see 4, think grouping. So here are the steps for grouping. First step, GCF, if any. There's no GCF among the 4 here. This last constant does not have an x, so there's no variable in common. This first one here has a coefficient of 1, so taking out a GCF of 1 doesn't really do us any good, so there's no GCF, but we have to look. Now, my first step here is to draw a dotted line between the 2 middle terms. Some teachers teach to put parentheses, and that's fine, but you have to be very careful as to where you put the parentheses and especially how you treat it when you have a negative here on the second half. So what I do, instead of drawing parentheses right away, I just kind of draw a dotted line down the middle, and that visually separates the 2 pairs of terms. Hence, that's why we need 4 for grouping. We group it evenly into 2 pairs, 2 here on the left, 2 here on the right. Now, there was not a GCF among all 4 terms. However, we're going to factor out a GCF from the pairs separately. And there is a hint. We're going to bring down that middle sign, and I'll talk about that in a second. So if we look to the left of our dotted line, we have an x cubed here and an x squared, so it has a GCF of an x squared. And if you divide that out, we would be left with an x minus 4. Now with the second set, notice you're starting with a negative. And remember, if your leading coefficient is negative, it's good to take out a negative GCF. So we're going to go ahead and take out a negative 3, and again we'll be left with an x minus 4. Notice that both of these binomials are alike, so we're going to use the method we did on the previous page. If for some reason you get like an x plus 4 here, check a couple of things. One, did you use the same sign there in the front, either a minus or a plus? And also, when you factored out that negative 3, did you take into consideration that a negative 3 times a negative 4 will give you that positive 12. Some people just bring down that sign here and they're not focusing on the distributive property when you're factoring out that negative. So if you're pretty confident you factored the first one correctly, you know your goal is for this binomial to be the same. So double check your signs so both of these match. Now we're going to factor out that binomial that's in common. So there's the x minus 4, leaving us with the x plus 2 and the x minus 3 for our second binomial factor. Yay! So here's another example. We have 4 terms. There's no GCF. You might notice that the 2 can be combined here in the middle because they're like terms. That's going to happen sometimes, and sometimes you can factor it using a trinomial method, but if it's already split up in 4, might as well try it with a grouping method. So we're going to split it down the middle. GCF on the first half would be a 2x, leaving us with an x plus 3. Now, on the second half, your front runner there is plus, a positive, so we're going to take out a positive GCF, but notice, really there's no GCF between x and plus 3 other than 1. So you can go ahead and put parentheses around the x plus 3 to remind yourself, I've looked for a GCF, this is factored as much as it can go, and so it's a binomial by itself, the x plus 3. Notice the 2 are alike. Also here, a lot of people stop and they go, oh, I've done my 2 GCF factorings, I'm done. But you've got to remember to bring down this sign, and this is your hint that you're not done. Everything has to be multiplied to be factored. Remember, factors are multiplied. So if you still have a plus or minus here, then you're not done. So the x plus 3's that you have in common becomes one of your factor. You've factored it out, and that leaves you with the 2x plus, what's that understood number there in the front if you don't see it? It's an understood 1. So if you need to write it in, don't worry about it. Write it in so you have that visual, and then both of those represent your second binomial factor. Yay! All right, so now you try. Here are 2 examples, 4 terms. I didn't give you any GCFs. I just want you to practice the grouping right now. So pause the video when you're ready, try these 2, and then hit play again when you're ready to take a look at how you did. Okay, let's see how you did on the grouping as I twist my pin. How did that happen? I'm twisting my pin here. Okay, so first we have to look for GCF among all 4. We do not have a GCF, but we had to look. There are 4 terms. That's our hint to factor by grouping. So first thing we're going to do is we're going to kind of group these into 2 and 2. Notice I put the hash mark to the left of this plus sign because this is going to help us determine what kind of factor we're going to take out, whether a GCF positive or negative. So on the first 2, we have a GCF of a 2y, leaving us with a y minus 5. On the second 2, we're going to take out a positive GCF, since our front runner was a plus, a positive. And the second 2 have a 7 and an x in common, leaving us with a y minus 5. So we do want to double check. Looky there, our binomials are alike. If they're not, double check your signs and make sure you took out the largest GCF. So that binomial in common becomes one of our factors. And the other factor comes from these GCFs that we took out. So our other factor is a 2y plus 7x. Okay, let's take a look at the next one. Again, there's no GCF, there's no variable here, there's no coefficient other than 1. We have 4 terms, hint that we're using grouping. So let's group them into 2 and 2. And remember, this sign here helps us determine what kind of GCF we're going to take out, what that middle sign is going to be. So the first 2, the AB plus 3B, have a GCF of B, leaving us with A plus 3. We're going to take out a negative GCF from the second 2. They have a 2 in common, leaving us with an A plus 3. Need to be careful with your signs here. Sometimes people leave this as an A minus 3 because they look up here and see that it was a negative 6. But remember, we took out a negative 2. If you were to distribute that back in, we'd have a negative 2A minus 6. Negative 2 times a positive 3 is a negative 6. Luckily for us, the binomials are alike. So that leaves us with a plus 3 as one of our factors. And then our other factors, factor, is made up from our GCFs, b minus 2. Not bad, huh? Good. Hopefully you saw where you made your errors if you had any. So how did you do? Did you remember to split it down the middle? Did you remember to bring down the signs? Did you find the binomial in common, the other two to get the other binomial? Double check and see how you did. If you made any errors, be sure and correct them. A couple of things to remember. Even though we didn't have any GCFs here, we still have to look for it. Always, always, always. First step. Also, we need 4 terms to factor by grouping. We'll talk about trinomials here in the next segment. So if you have any questions, feel free to watch the video again, look at other videos, ask your teacher, ask your tutor, ask your friends. Don't let your pride keep you from passing. Ask questions, because I guarantee you, you're not the only one. You may just be the only one brave enough to ask, okay? So come back next time, take a look at factoring trinomials with the first coefficient of 1. See you soon. Hi, welcome back. Now we're going to factor quadratic expressions where the leading coefficient is 1. Okay, so we have a trinomial. Front runner here is 1. Now, in order to do this, I want to review the FOIL method. Again, I don't really care about the FOIL method as far as multiplying goes, because all of those are multiplied the same. But that pattern really helps us when we go backwards and factor. So let's take a look. Suppose we have the binomial x plus 3 times the binomial x plus 12. Well, first we multiply the first terms, x to the x, and we get x squared. Hence the f, first terms. Then the x gets multiplied by the 12. Those are considered the outside or outer terms. That gives us a 12x, O for the outside. Now we have to distribute the 3. The 3 goes to the x. These are considered the inside terms and gives us a 3x, I for inside. And finally, the 3 gets multiplied by the 12. Those are the last terms in each binomial to give us a 36. FOIL, first, outside, inside, and last. Notice the pattern. These two middle terms combine and we get 12x plus 3x, which is 15x. So here's our trinomial. The x squared here is a result of multiplying the first terms. The 36 here, the last, we got from multiplying the last. So the first in our trinomial, we got from multiplying the firsts. The last in our trinomial, we got from multiplying the lasts. The middle is from combining the outside and the inside terms that we got. One thing I want you to notice in our result, this last number here is 36. We got that when we multiplied 3 and 12. The middle number here of 15, we got from adding those numbers, 3 and 12. So that's the pattern that we're looking for. We're going to start here and go backwards. We are going to look for 2 items that will multiply and give us this first term, x and x. We're going to look for 2 numbers that multiply and give us 36. Well, there's a lot of numbers that multiply and give us 36. Not just 3 and 12. We got 1 and 36, 2 and 18, 6 and 6, a whole lot of different combinations. We need to find the pair that will also add to 15. That's where the pattern comes in handy. So let's take a look here. X squared plus 15x plus 36. The first terms multiply to give us x squared. That's where the x times x comes in. The last terms multiply to give us 36, but add to give us 15. So we're going to look for factors of the last number that add to the middle number. Now, some of you may have learned what's called like the diamond method, where you draw like a big X and you write 36 on top and the 15 on bottom, and then you try different pairs of numbers to see which ones work. Some of you rock at that, and that's awesome. Me, oftentimes the pair that I need is the one pair I don't think of. So what I do is I take this 36 and I list all of the factors, but I list them methodically. I start with 1 times 36, then 2 times 36, 3 times 12, 4 times 9. 5 is not a factor of 36. Notice 36 does not end in 5 or 0. And then 6 times 6. And then once you start to repeat, you know you're done. But this way I know I have every single factor. I've gone down the list. Then I look for the pair that adds to the 15, the 3 and the 12. 3 plus 12 also gives us 15. So they multiply to give us 36, and they add to give us 15. So if you can't find it, like I said, the other methods are perfect, but if you can't find it, go ahead and list them, and it might help. So these are the two factors we're going to use in here, x plus 3, x plus 12. And remember, you can always multiply these out to just double check that it does in fact equal your original trinomial. So here's another example. It's a trinomial. There's no GCF. Your first coefficient is 1. So that means I can go straight to the x times x, which gives us the x squared. Now I want to find factors of negative 70 that add to a negative 9. Now the 70 is negative, which means one of our factors has to be negative. Only a negative times a positive is going to give you a negative number. So I just start with the left-hand side always being negative. Negative 1 times 70, negative 2 times 35. 3 does not divide in there, 4 does not go in there. We have negative 5 times 14 and negative 7 times 10. 8 doesn't go in there, 9 doesn't divide in there, and then we start to repeat. Well, you may notice if we look at watch your signs. If we look at negative 5 times 14, well, they add to give us a positive 9. But remember, we want a negative 9 because it's a minus 9x here, so we want a negative 9. If you end up with the right number but the wrong sign, change your signs. So instead of negative 5 and a positive 14, we're going to change our signs to a positive 5 and a negative 14. So that gives us the negative 9. And these are the two numbers we're going to use here in our factors. So we have a positive 5, so plus 5, and a minus 14. So just something to think about as far as the signs go, because oftentimes it's either your multiplication tables or it's your sign rules that will hold you back. So if your last number is positive, you're going to have the same signs. For example, here, if you've got a positive 6 adding to a positive 5, then I'm going to use a positive 2 and a positive 3, because positive 2 times positive 3 gives me a positive 6, and it also adds to 5. But if I had the exact same problem, notice it has to multiply to give me a positive 6, but it has to add to give me a negative 5. So it's not just a positive times a positive that gives you a positive, but negative times a negative also gives you a positive. So this guy here will help you determine what those signs need to be. So we're going to use a negative 2 and a negative 3 here. So if your last number is positive, you have to have a positive times a positive or a negative times a negative. So the signs are going to be the same. Likewise, if your last number is negative, you have to have different signs, because only a positive times a negative or negative times a positive is going to give you a negative product. So x squared plus 5x minus 6, we're going to use a positive 6 and a negative 1. They multiply to give me a negative 6, but they add to give me a positive 5. Versus x squared minus 5x minus 6. Well, they multiply to give me a negative, so I know my signs are different, but they have to add to a negative 5 this time, so I'm going to use a negative 6 and a positive 1. So remember, your sign tools are really important here. Now, what if there is a GCF? No problem. Remember, we have to look for that first. So here, there's not a variable in common, because this last number doesn't have a variable, but all of the coefficients are divisible by 8. So we have a GCF of 8. But this is what a lot of students want to do. They want to take out the 8 and go straight to the two binomials. This is too hard. I have trouble doing this, okay? Believe me, after 3 o'clock, my brain is toast. I can't think. So if you're taking an afternoon class and you're like me, this is definitely too tough. But oftentimes, it's not intuitive. You know this is what your result is supposed to look like, but there's a middle step that you're missing. So first, always factor out the GCF to see what is left. So remember the distributive property backwards. So you want to see here's the 8 and then what you have left over after you divide out that 8. Now factor this trinomial that's in parentheses. Your 8's still going to be there, but you want to determine what are the two binomials you get from the trinomial inside the parentheses. So now your first coefficient is 1 of that y squared. So y times y would give you the y squared. And we want factors of a positive 3, so our signs are the same, that add to a negative 4. So both signs are going to be negative. So negative 1 and a negative 3. If you wrote negative 3 first and negative 1 second, that's fine. The order doesn't matter. Now you try. Here are 3 different examples. I want you to go ahead and pause the video and then try them. Once you're done and you want to see how you did, hit play and we'll go over them together. So we are now one step closer to mastering all the factoring techniques. This one, we've got a trinomial where your first coefficient is 1, so we can go straight to y times y, because remember the first terms will multiply to give you the y squared. Now we need to figure out what these last two guys are going to be. They have to multiply and give us the last guy there. So what choices do we have for 24? Well, we have 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 doesn't go, and then once you hit 6, you start to repeat again. So now we're looking for the factor pairs that would also add to a negative 24. Well, the problem here is I've written all of these down as positives. Well, two positives multiply to give me a positive number, but they're not going to add to give me a negative. So what must both of these signs be? Negative. So negative times a negative, negative times a negative, negative times a negative, negative times a negative. Now which pair add up to 14? Good. The negative 2 and negative 12, because negative 2 plus a negative 12 also gives you a negative 14. Negative 2, negative 12. So that's the pair that we want. And you can always double check. The outside multiplies and gives you a negative 12y. Inside multiplies to gives you a negative 2y. So when you combine the outside and inside, we will get the negative 14y. So our result, we'll write it a little neater. Y minus 2 times y minus 12. All right, let's take a look at the second one. 3x squared plus 3x minus 36. Notice we have a GCF here of a 3. So if we factor out the 3 first, we would be left with x squared plus x minus 12. Now we can go and factor into the two binomials. X times x, factors of negative 12. One of them has to be negative, so we've got negative 1 times 12, negative 2 times 6, negative 3 times 4, and then negative 4, and we start to repeat. So of these pairs, the negative 3 and 4 would add to this middle term of positive 1, because negative 3 plus 4, that's a nice little extra piece there. Negative 3 plus 4 would give us 1. So there's our result. Completely factored. Last but not least, C, we have x squared plus 7x plus 6. We can go to x times x. And we want factors of a positive 6 that add to a positive 7. So 1 plus 6 and 2 times 3. So 1 plus 6 works. Plus 1 and plus 6. Double check, see how you did. So how did you do? Factoring can be fun, but it can also be frustrating. So be sure that you take your time and practice. So a few things to remember. GCF is always the first step to factoring. And this x times x method, where factors of the last add to the middle, only works when your first coefficient, your leading coefficient, is 1. In other words, you do not see a number in front of the x squared. Thanks for watching, and if you have any other questions, please don't hesitate to watch the video again. Go look for other videos. Believe me, I won't be offended. There's some great resources out there. Also, ask your teacher, ask your tutor, ask your friends. Don't let your pride keep you from passing. So hopefully we'll see you again soon. Welcome back. Today we're going to take a look at factoring quadratic expressions again, only this time when the leading coefficient is not 1. In other words, we're going to have a number here in the front. But let's do a quick review. The FOIL method here, remember we're going to multiply the first, outside, inside, and last. When we do, we get these 4 terms, x squared plus 12x plus 3x plus 36. The 2 middle terms combine, and we get x squared plus 15x plus 36. Noticing the pattern here, when your first coefficient is 1, and those get distributed with this one here and this one here, our 2 middle terms have the same coefficients as the 3 and the 12. So the 3 and the 12 multiply to give us 36, add to the 15. So when we factor with a leading coefficient of 1, we're going to use that pattern. We're going to find factors of 36, and we're going to look for the pair that add to 15, and we'll use the 3 and the 12. Today, we're going to take a look at the FOIL method and factoring when your first coefficient is not 1. So when we multiply the firsts here, we get a 2x squared, and now that 2 is going to get multiplied by the 12 and give us a 24x. And then distribute the 3, we get a 3x and a 36. The 2 middle terms still combine, and we'll end up with 2x squared plus 27x plus 36. But notice, there are no factors of 36 that add to the 27. So we have to use a different method when we have a coefficient other than 1 that's going to get multiplied in. So when we have a leading coefficient other than 1, there are many different ways of factoring them, and teachers do different stuff. They use boxes, they take out a GCF, put 1 in. But I've picked the 2 probably most common methods. So we can use either the trial and error, which is kind of what it sounds like. Try it, didn't work, try something else. Or what I call the multiply, split, and group method, affectionately known as MSG. So let's first take a look at trial and error. 2x squared plus 19x plus 24. Notice that there's no GCF among all 3. We want to find the 2 binomials that work. So let's recall the pattern of the FOIL. The first terms in the 2 binomials will multiply to give us the first term here, the 2x squared. So our only choice is going to be 2x and x. Also, the last terms multiply to give us the last term. So these 2 terms here are going to multiply to give us the 24. Here are all of our choices. Notice none of them add up to the 19. So we need to use the fact that the outside and inside should add to the middle. Now, here are a couple of hints so we don't have to try all 4 pairs and all of them in different orders. The first thing is, for us, this 1 and 24 is going to be too big because the outside and inside have to add up to 19, and you've already got a 24. So we can mark out the 1 and 24. The second hint is if the original does not have a GCF, neither will the factors. So since our original did not have a GCF, this first factor here cannot have an even number in it because then it would have a GCF of a 2. So that's going to take out the 2 and 12 and the 4 and 6 because both of those are even. The only pairing we have left is the 3 and the 8. Now, again, we're not sure which order except for the fact that the 8 is also even. So we cannot put the 8 in with the 2. We have to put in the 3 and then the 8. If for some reason you have some other pairs, other factor pairs that didn't get excluded with these hints, try them out. For example, here we want to check it. The inside multiplies to give us 3x, The outside multiplies to give us 16x, and they do in fact add up to 19x, so they work. If they didn't work, you erase them, either try them in a different order or try a different pair. Hence the name trial and error. Now, the second method, the multiply, split, and group, or MSG, I kind of made up that name because it sort of describes the steps of what you do. Some books call it the AC method or the multiply method, or you may be using a diamond method, but they're all the same thing, just so you know. But I call it the multiply, split, and group because it's easier to remember. So we're going to use the same example. Now let's look at the multiply step. We're going to multiply the first and the last numbers, in this case the 2 and 24. A big hint from me to you, first of all, I want you to tap the 2 and 24. This is called muscle memory. If you get nervous on the test, sometimes your muscles will remember what to do before your brain actually accesses it. Kind of like when you're walking home or driving home, you get to your front door and you're like, I don't even remember getting here. It's because you've done it so often, your body automatically knows what to do. Same thing, okay? Muscle memory. Then I want you to physically write down 2 times 24. That's a visual, noticing the 2 numbers you use are the 2 numbers on the outside, and then say it out loud to yourself. 2 and 24 equals 48, gives you an auditory. So the more senses you use doing your homework, the more you're able to access the information when you're nervous, say when you're taking a test. A little tip from your Aunt Lainey. Okay, so now let's find factors of 48. Listed them all here, that add to the middle, to the 19. The 3 and the 16 work. Now, we're not going to plug them directly into the binomial. We're going to use them in a different way, and that's where the split part comes. We're going to use the 3 and 16 to rewrite the middle term as 2 like terms. In other words, we're going to keep the 2x squared, we're going to keep the 24, and we're going to split the 19 using the 3 and 16. 3x plus 16x. So we haven't changed the value of anything here. But how many terms do we have? 4. Excellent. So that's where the grouping comes in. We have 4 terms, so now we're going to factor using grouping. So let's go ahead and split down the middle. We're going to factor out a GCF of x from the first 2. We're going to factor out a GCF of a positive 8 from the second 2. Notice our 2 binomials are alike, the 2x plus 3. So let's factor out the 2x plus 3, and that leaves us with the x plus 8. Yay! So trial and error is awesome and it's fast, but sometimes when you get stuck, it's nice to have this method in your back pocket as well. So here are 3 that I want you guys to try. Go ahead and pause the video when you're ready. And if you've got the time and the space, try both methods. Try the trial and error and try the multiply, split, and group. They're both valid methods. Sometimes the trial and error is faster, but it's nice to have both in your back pocket. So try them out, and when you're done, ready to see how you did, go ahead and hit play. Okay, let's see how you did. We've got a quadratic equation. Our front runner is not 1, we have a 4. And also there is no GCF, so we can use the trial and error method or multiply, split, and group. So for the next 3, let's practice the multiply, split, and group since there's more steps to it. We're going to multiply the 4 times the negative 6, those outside numbers. That gives us a negative 24. Factors of a negative 24, negative 1 times 24, negative 2 times 12, negative 3 times 8, negative 4 times 6. So we've done the multiply. Now we need to split by finding the 2 factors that add to a positive 5. Negative 3 and 8 work. They add to 5, and we don't have to switch the signs. So we're going to keep the 4, y squared. We're going to keep the negative 6, but we are going to split that 5y into 2 like terms using the negative 3 and the positive 8. Now we've done the multiply and the split, it's time to group now that we have 4 terms. So we're going to split it down the middle, take out a GCF from the first 2, which is a y, leaving us with 4y minus 3. The second 2 has a GCF of a positive 2, again leaving us with 4y minus 3. Our 2 binomials are alike, therefore we're going to factor it out, the 4y minus 3, leaving us with the y and the plus 2 for our other binomial factor. Now, if you use trial and error here, that's great. Odds are you probably started with a 2y times a 2y, but notice they were both even, so there were a lot of these choices that you could mark out because they were all even and you didn't have a GCF, leaving you with 3 and 8, but then when you tried it, you would notice the 3 and 8 do not work either. And then you'd have to have gone to the 4y times y. Let's take a look at B. We have 20x squared minus 17x plus 3. There is no GCF. Using the multiply, split, and group, we would multiply 20 times a positive 3, which gives us a positive 60. But it adds to a negative 17. So to multiply to give us a positive, but add to give us a negative, we would have two negative factors. So let's see, negative 1 times a negative 60. Negative 2 times a negative 30, negative 3 times a negative 20, negative 4 times a negative 15, negative 5 times negative 12. I'm spreading out here a little bit. Negative 6 times negative 10. 7 does not divide in, 8 does not divide in, 9 does not divide in, and then we would repeat. So the pair that would add to a negative 17 would be negative 5 times negative 12. So again, we're going to keep the first term, the 20x squared. We're going to keep the last term of a positive 3. We're going to split that middle term using these as coefficients, the negative 5x and the negative 12x. Now that we have 4 terms, we do our grouping. We're going to split it down the middle. First 2 has a GCF of 5x, leaving us with 4x minus 1. Second 2 have a negative 3 in common, leaving us with a 4x minus 1. Double check your signs. Then they had a 4x minus 1 in common, leaving us with a 5x minus 3 as our second binomial. Last but not least, number 9, we do have a trinomial. Our front runner is 1. However, we do have a GCF. There is a 3 in common. So if we factor out a 3, that would leave us with a 3x squared plus 14x plus 8. Now, for some of you, the GCF of 3 here out to the side might get a little confusing. So I do allow my students to bring down a little arrow, write down their 3, and go ahead and put in the 2 binomials that we'll be looking for. That way they don't forget it when they get to their answer at the very end, but it's not in their way while they're factoring. Because remember, every line should be equal to the one above it, so technically that 3 should be carried down all the time. But if it visually gets in your way, ask your teacher if you can, make some sort of notation that it carries throughout, but then just put it down at the end so you don't forget it. So now we're going to multiply this 3 and this 8. For our multiply, split, and group, and we get a negative, and we get a 24. Factors are 1 times 24, 2 times 12, 3 times 8, and a 4 times 6. Factors that add to 14, this time we got 2 and 12. So we're going to keep the 3x squared, we're going to keep the plus 8, and then we're going to split the 14x using the 2x and the 12 with an x. Now that we have 4 terms, we can split the middle and group. And we've got an x as our GCF for the first 2, leaving us with a 3x plus 2. And the second group, we have a 4 in common, leaving us with a 3x plus 2. So we have a 3x plus 2 in common. We can factor that out, leaving us also with an x plus 4. And there's our result. So how did you do? Good, I hope. If you made a couple of errors, that's fine. Find out what you did wrong, correct it, and then you know kind of what mistakes to look for in the future, especially on your test, okay? So to remember a few things about factoring, once you have your polynomial in descending powers, look for a GCF. It may or may not have one, but you need to look first. Then count the terms. If you have 4 terms, that means you can use grouping. 3 terms, if you don't have a coefficient other than 1, or if you do have a coefficient of 1, you can use the trial and error, or the multiply, split, and group method, affectionately known as the MSG. So hopefully you didn't find factoring too painful. This is a sticking point for a lot of students. So don't feel like you should have it mastered as quickly as you did some of the earlier material in your class. It's going to take some time, especially if you're not as quick on your multiplication facts. Just know that ahead of time. This is going to take you a little bit longer, but that's okay. All right? So if you have any questions, you can watch the video again, look for other videos, ask your teacher, ask your tutor, ask your friends, but ask somebody. Get some help. Don't wait until the day before the test to go, I didn't get this. It's too late by then. As soon as you're stuck, get help. Don't let your pride keep you from passing. Enjoy yourself, and hopefully we'll see you again soon. Hi. Today we're going to look at factoring the difference of two squares. So difference, remember, means subtraction. We've got two terms and both of them are perfect squares. Between you and me, these are my students' favorites. They want 100 of these on the test. If this is all they had to factor, they'd be very happy. So I think you're going to like this section. But before we get into it too much, I want to compare two different types of problems. The first one is a binomial squared, where you have a single binomial like this one, x minus 3 taken to the power of 2, versus conjugates, where you have two binomials that look almost identical except for their operations. One is addition and one is subtraction. When you multiply these two out, you get two different results. So let's focus first on the binomial squared. If we were to expand it and distribute, FOIL method if you will, notice in the middle here we get a minus 3x, which will combine and give us a negative 6x there in the middle. So when you distribute here, you will end up with what we call a perfect square trinomial. You can look for a pattern for perfect square trinomials when you go to factor and work it backwards, but really also the trial and error, the multiply, split, and group, any other method that works for trinomials also work for these. So I don't spend my kids' brains memorizing that pattern really. I just let them use one of the other methods. But with conjugates, these are kind of fun. Notice what happens when we distribute here. When we distribute and do the FOIL, we get x squared minus 3x plus 3x minus 9. Because they're identical, as far as the two pieces, the x and the 3 and the 3, but their operations are opposites, one addition, one subtraction, we will always have opposite terms here in the middle. One minus, one positive, and they will always add up to 0, and we get what we call a difference of two squares. The cool thing about these is difference of two squares, when we go to factor, there's not a whole lot of work in between. So difference of two squares factor into conjugates. Two binomials using their square roots, one addition, one subtraction, and it doesn't matter which one you put first. So for example, x squared minus 16, you've got two terms. It's subtraction. They're both perfect squares. The square root of x squared is just x. Square root of 16 is 4. So we're going to have an x plus 4 and an x minus 4. Cool, huh? My favorite. Love these. All right, let's do it again. Difference of two squares. You've got perfect squares here, 4y squared. The square root would be 2y. Square root of 81 would be 9. So we're going to have a 2y minus 9 and a 2y plus 9. Changed up the signs just so you can see that it doesn't really matter which one you write first. But there's no work to it. These are the only factoring problems, by the way. I don't make my students show me work. It's like you just write it down. Now, it does not work if it is a sum of two squares. Okay, it has to be a difference of two squares. It doesn't work with addition if you've got squares. So x squared plus 25, remember you have to have those opposite signs in order for those two middle terms to add to 0. We don't have opposite signs here, so it's not factorable. If you tried x plus 5 and x plus 5, or x minus 5 and x minus 5, that's going to give you the first type of problem that we had, the perfect square trinomial. Okay, so this one is not factorable. So don't forget your GCF. For example, here you go, oh, okay, I've got a difference, I've got two terms, but they're not perfect squares. However, they both have a factor of 3. So we can factor out the 3 first That leaves us with x squared minus 25. This is a perfect square. So now we can factor this binomial. Here's our GCF on the outside, and the x squared minus 25, using their square roots, gives us x minus 5 and x plus 5. Now you try. Here are 3 problems. Give them a shot. Go ahead and hit pause. And then when you're ready to see how you did, hit play again. All right, did you try them? Let's see how you did. Notice we have 2 terms. There's no GCF. It is subtraction, so we have a difference, and both of them are perfect squares. So we can go straight to our 2 binomials. A y times y will give us y squared. The square root of 36 is 6, giving us 6 times 6. And we're going to have conjugates, 1 plus and 1 minus. And it doesn't matter if you write the minus 1 first and the positive 1 second. Remember, it's multiplication, and the order doesn't matter with multiplication. So both of these are correct. Smiley face. Love these, right? So let's try the next one. We have 2x squared minus 98. We have 2 terms. It is a difference, but are they perfect squares? They're not, but we do have a GCF of 2. They're both even. So if we factor out a 2 first, we get x squared minus 49, and now that 49 is a perfect square. So we still have to have the 2 in our binomial. We have an x times x to give us x squared, and a 7 times 7 to give us the 49, 1 positive, 1 negative. Last but not least, x squared plus 16. We've got 2 terms, no GCF. They're both perfect squares, but it's addition. Remember, in order to factor a difference of 2 squares, we have to have opposite signs, a positive and a negative, to get rid of that extra term. And we can't do that when we're multiplying to get a positive number. Either they're both positive or they're both negative. Therefore, this is not factorable. Your teacher may have you say that it's prime. In other words, the only factors are itself and 1. And there's no need to factor out of 1. So, how did you do? You liked this section, didn't you? Okay. If you know your square roots, you'll feel comfortable. If not, you may have to work with them a little bit, but my students love this because there's not a whole lot of work with it. So things to remember, your steps for factoring. Always look for GCF and then count the terms. If there's 4 terms, you can use grouping. If there's 3 terms, you can do either trial and error or multiply, split, and group. Or if there's another method that your teacher taught you that you love, use it, go for it. Now, if there's 2 terms, we're going to look to see if it is a difference of 2 squares. Okay, so it has to be subtraction. So difference of 2 squares factor into conjugates, 1 plus and 1 minus. Or a sum or difference of cubes we'll teach you in the next video. Okay, so have a good time. Do all of your difference of 2 squares, and we'll see you for the next video. Hi, welcome to the last video that we're doing on factoring. This one is on factoring the sum or difference of 2 cubes. This is kind of a generic form here. You've got 2 terms here, both being cubed, and it doesn't matter if it's addition or subtraction. Now, unfortunately, with cubes, there's a pattern to remember. So we're going to show it to you, but it's not that bad. Trust me. So here's an example. X cubed plus 64. 64 is actually 4 cubed. So the first thing we're going to do is rewrite as a base to a cube. So x is x cubed and 64 is 4 cubed. Then we're going to write parentheses for both a binomial and a trinomial. So think when you're doing cubes, it's a power of 3. So in this case, one of your factors is going to be a trinomial with 3 terms. Now we're going to write in the signs. And I know this seems counterintuitive, but again, just follow the pattern. We're going to write in the signs that separate the terms in the binomial and the trinomial using the same, opposite, and always positive. Well, we started with an addition, so we're going to bring down a plus sign. That's the same as what we started with to separate the terms in the binomial. And then the opposite of that is subtraction, and then the last one is always positive. There's an acronym to help you remember that. SOAP, SOAP, for same, opposite, always positive. Think of a cube of soap. Now we're going to drop the bases into the binomial. So we're going to bring in the x and we're going to bring in the 4. There's your binomial term. Now we're going to fill in the first and last of the trinomial by squaring the first and last. So take the x, square it, and we get x squared, which makes sense. X times x squared is going to give us our x cubed. Same thing with the 4. Square it and we get 16. 4 times 16 gives us our 64. Yay! So we have our first and our last terms. So now we're going to multiply the x and the 4 to give us our middle term. So x times 4 gives us 4x. And there's our middle term, which is one of the reasons why we did the signs first, so you wouldn't get confused whether it was a positive 4x or a negative 4x. And there's our answer. So let's try another example. This one's a little bit more complicated. We do have cubes, so we're going to rewrite the 8 as a 2 and then an x being cubed. So there's our base of 2x. The 125y to the 6th is actually 5y squared being cubed. 5 cubed is the 125. Y squared, if you cubed it, would give you y to the 6th. So rewrite your bases as something taken to the power of 3. Then we put in our parentheses, binomial and then a trinomial. Then our signs, same, opposite, always positive. And then we're going to drop our bases into the binomial, 2x and then the 5y squared. And then we're going to square the 2x to get our first, and we get 4x squared. We're going to square the 5y squared to get our last, which is 25y to the 4th, and then multiply the 2x and the 5y squared to get 10xy squared in the middle. And there's our final answer for that one. So you do have to remember the pattern. So here are 2 problems that I want you guys to try. Don't forget to rewrite them as bases cubed, binomial, trinomial, SOAP, and then drop them down, square them, and then multiply. So when you're ready, pause the video, go ahead and work them out, and when you want to see how you did, hit play again. Are you ready to take a look? All right, we've got 2 terms, so we're looking to see, is it a difference of 2 squares or is it a sum or difference of cubes? We do have a difference, it is subtraction, but we don't have a y squared, it's a y cubed. 8 is also a cubed term, so we can rewrite it as bases cubed. We have a y cubed minus a 2 cubed. So here's our bases, the 2 and the y. And remember, with a cube, one of our factors has to be a trinomial. So we're going to have a binomial and a trinomial. And remember our signs. We're going to start with the same as what we started with, the opposite of what we started with, and the last one is always going to be positive. So you can remember the acronym SOAP, same, opposite, always positive. Now for your binomial, remember we just drop down the 2 bases, the y and 2, and then we square those 2 to get our first and our last. Y times y squared would give us the y cubed. 2 times 2 squared would give us the 2 cubed, but 2 squared is 4. So square the first, square the last. And now we need to multiply the 2 bases together, which gives us a 2y there in the middle. So this seems to be the one that most people forget, is to multiply the 2 together to get the middle. But this is our final result. Whoop. So let's look at the second one. This one looks more complicated, but it's still the same thing. We have 2 terms, they're cubes, but this time they're being added. So rewrite the bases. That 27 is a 3, and then we have the x, both of those being cubed, plus the 64 is a 4 being cubed. So there's our 2 bases. So here's our binomial, and here's our trinomial. So remember our acronym for our signs, same, opposite, always positive. So we started with a plus sign, so it's going to be the same, plus the opposite of the plus, and then always positive. Then we drop the bases, and if you look, your binomial, if you rewrite them as bases being cubed, your first binomial is almost like you're just hiding those exponents, 3x plus 4. If it was a minus, it would be a minus. Okay, so be sure that you rewrite those as bases being cubed. So 3x and 4. So 3x squared is a 9x squared. And then our 4 squared would give us a 16 there at the end. So we've squared our first and our last. And now we have to multiply these two together to get our middle term. 3x times 4 gives us a 12x. So again, remember the pattern. So how did you do on those two? Notice you probably had to keep your notes nearby so you can remember the pattern and remember what to do in order to factor them, and that's fine. The more you do, the less you're going to need your notes, okay? So if you need to refer back to them, that's okay. So a few things to remember again about factoring. Let's sum everything together. First of all, look for a GCF. May have one, may not, but you have to take it out if there is one. Also count your terms. If you have 4 terms, then we can factor by grouping. If there's 3 terms, we can use trial and error or the multiply, split, and group method. 2 terms, now we've got 2 things to look for. Either a difference of 2 squares, which means we'll use conjugates, x minus a, x plus a, or we can have the sum or difference of cubes, which means we're going to use a binomial and a trinomial, SOAP for our signs, and then we do the drop, the square, and the multiply. So you're done with the factoring. Yay! Now you can get on with your life. But hopefully it wasn't that bad. And don't forget, if you have any questions, watch the video again, look for other videos, but ask somebody, your friends, your teacher, your tutors, somebody. Don't let your pride keep you from passing, okay? Thanks for watching, and hopefully we'll see you again soon. Hi, today we're going to take a look at solving quadratic equations by factoring. But let's remind ourselves what a quadratic equation is. It's a polynomial equation where your highest exponent is 2. So we've already learned how to solve linear equations, highest exponent of 1, in other words, you don't see the exponent, and quadratic, highest exponent now of 2. So what are the tools that we need? What skills do we need to have in order to solve using this method? First of all, need to be able to set an equation equal to 0. 0 is going to be very important to us here. Also, how to factor a polynomial. This seems to be a big issue for a lot of students, so if it is for you, you're not alone, okay? But if it takes you a little bit more time than somebody else, don't stress over it. Just keep practicing. And also, how to solve a linear equation. So if you have those 3 things mastered, then this method shouldn't be too big of a problem for you. All right, so let's take a look at an example. It's a quadratic equation, x squared minus x equals 12, but it's not set equal to 0. So we need to move that 12. So we're going to subtract 12 from both sides. Be careful here, common error sometimes, especially when students are nervous. They write the negative 12 over there and they just automatically combine it with whatever's on top of it. If they're not like terms, you can't combine them. So we'll just write it out, x squared minus x minus 12 equals 0. So here's kind of your thought process when you get to a test and you're really nervous. I'm solving. What is my goal when I'm solving? To get x equals a number. Just a single x equals a constant. We have 2 x's here, and they're not like terms, so we can't combine them into one x term, okay? I could try to get this x by itself, but I'm just going to end up with an x squared over here. That doesn't give me x equals a number. That will give me x equals something that has an x with it. So we need to somehow reduce this x squared down to a single x. So you think back to your tools, what have we learned that we can do with a trinomial? Factor. Because when you factor, you end up with an x and an x, which is what we want. So we're going to factor the left-hand side. We get x plus 3 times x minus 4. Now here's where the specialness of 0 comes in handy. When you have things being multiplied, factors being multiplied to equal 0, one of them has to be 0. The only way to multiply and get 0 is for something to be 0. 0 is the only number that's true for. So if we set each of these factors equal to 0, x plus 3 either equals 0 or the x minus 4 equals 0. Now we have 2 linear equations, and you know how to do that. So we're going to solve both of these linear equations. We're going to subtract 3 from both sides here, adding 4 to both sides there, and we get two solutions. X equals -3 and x equals 4. Two solutions is fine because we have a highest exponent of 2, so we can have up to 2 solutions. Linear, we only had a single x, therefore we would only get a single solution. Okay? So now I want you to try. Remember, set it equal to 0, factor, set each factor equal to 0, and solve. So go ahead and pause the video, and then when you're ready to take a look at some of the solutions and see how you did, hit play. All right, are we ready? Okay, we have a quadratic. It's already set equal to 0, so we're going to factor. Now we're going to factor a little quickly. If you're still having trouble with the factoring method, be sure that you look at the videos and get some more help. So let's see, factors in -6. We've got a -6 and a +1 set equal to 0. Now, what some people do, because it's a solving, sometimes they get so excited that they factored correctly, they stop. So be sure that you continue down the equals 0 to remind you that you're not done yet. You still have to solve. So we're going to set each linear equation equal to 0, x minus 6, and x plus 1 equaling to 0. And then we solve. Add 6 to both sides, and we get x equals 6. Subtract 1 from both sides, and we get x equals -1. So there are our two solutions. Remember, we have a highest exponent of 2, therefore we can have up to 2 solutions. For some of you, especially with the use of color, what might help as far as your notes is to highlight the fact that your highest exponent is 2 to remind you what kind of equation it is. Highlight the fact that it's set equal to 0 because it needs to be. And then maybe make note or write them in a different color, the two binomial parentheses, to help you remember that factoring is the first method that you want to try. Okay? Same thing here, you know, it's set equal to 0. We've got an exponent of 2, so we're going to try to factor the left-hand side. It's a little bit more involved here. We have a 3x and an x, and then factors of 12. Looks like we're going to have a 6 and a 2. Yep, double checking. Now we're going to set each linear equation equal to 0. So again, we have to know how to factor, we have to know how to solve linear equations. So we'll do this a little quickly. And now divide both sides by 3. So our first solution is a -2/3. But don't forget you have a second one. Subtract 6 from both sides, and we get x equals -6. And now the last one. What's the problem here? Your highest exponent is 2, but, you know, little frowny face, not equal to 0. Any kind of notation that will help you to remember come test time what's wrong with the equation, what needs to be fixed. We've got to set it equal to 0. So if we add 5 to both sides, let me show you a common mistake that I often see. Now on the right-hand side, -5 plus 5 does add up to 0, which is our goal. But when you throw the +5 over here, be careful because some people are tempted to combine these two merely because you wrote it underneath it, okay? They're not like terms, so we can't do that. But I see it, especially when people are nervous on a test. So just be aware of it and write them out left to right. We've got 2x squared minus 11x plus 5 equals 0. Now we can factor. What do we have? 2x and x. And that would give us a -1, -5. And now each of these need to be set equal to 0. Just to give us a little bit more room, I'm going to write them out here. 2x minus 1 equals 0. And x minus 5 equals 0. So on the first equation, if we add 1 to both sides, that will leave us with a 2x equals 1. Divide both sides by 2, and we get x equals 1/2. On the right equation, we add 5 to both sides of the equal sign, and we're left with x equals 5. 2 solutions. Make any notations that you need to that's going to help you when you study. So how did you do? Let's take a look at some of the common stumbling blocks for students when they're solving using this method. First of all, did you set it equal to 0? Remember, 0 is the only special number that's going to work for. Did you factor it correctly? Again, this is usually the biggest stumbling block, especially if you're weak in your multiplication tables, and a lot of people are. So it's going to take you some time. But if it takes you longer than somebody else, who cares? I mean, really. I always told myself I'm going to be the last one to finish my test. That way I know that I'm focused and I'll let everybody else do what they want to do, and that was kind of my goal in test taking. So maybe that'll work for you, but don't stress. If it takes you a little bit of time, go for it. Then, did you set each factor equal to 0? And then did you solve each of those correctly? So let's remember a few things. Does it have an x squared? If that is your highest exponent, then it's quadratic. You need to set it equal to 0, factor if possible, and if it's not, we'll show you a different method later that will work. Did you set each factor equal to 0 and then solve? So thanks for watching. I hope this helped. But remember, if you still need more help, ask your teachers, ask your friends, look for more videos. There are resources out there. Don't let your pride keep you from passing. You're not alone in this, okay? Okay. Hopefully we'll see you again soon. Welcome back. So you're needing a little bit of help with solving rational equations. Let's review what a rational equation is. A rational is a fraction that has polynomials in the top and the bottom. Basically, you're going to see some x's or y's down in the denominator. Remember, when you're trying to solve an equation, you want to get x equals a number, not 1 over x. So that's your obstacle first, is that you have a fraction. So what are the tools that we need in order to solve these? 1, how to find the LCD of a rational, which I'm going to show you here in a second. We'll review it. Also how to distribute, and then how to solve linear and quadratic equations. So once you have all of these in your tool bag, hopefully 2 and 3 are there, 1 we're going to review here in a second, then solving rational equations is just a matter of undoing those obstacles that we've talked about, okay? So, least common denominator, often called the LCD. In fancy terms, it's the common multiple of all the denominators. What does that mean to you and I? To you and I? To you and me, too. Yeah, preposition, right? Yeah, doctorate. Anyway, so common multiple of all denominators, what does that mean to you and me? It means that every factor in every denominator is going to be seen in that LCD, but we have to be careful. If we just factor everything in the denominator and put them all down, our denominator may be huge, and we don't want that. We want the least, we want the tiniest one. It's easier to work with, easier to multiply, easier to add, whatever we're going to be doing. So the warning is to be careful. Some of them may overlap. In other words, we might share factors. And I'll give you an example. This is definitely a rational equation. Why? We've got fractions, and you have some variables down here in the denominator. That's the bottom. So in order to find the LCD, we want to factor the denominators. Well, these last two fractions are already simplified. We can't factor that any further. We got the y minus 4 and the y minus 2. This trinomial here, however, can be factored further. So we have a y minus 4 and y minus 2 here. That's actually very nice because it's similar to some of the denominators that we already have. So remember, the LCD has all of those factors represented. So we are going to represent every factor in the denominator, in each denominator, in the LCD. So let's start with the one on the left. So in this denominator here, it includes a y minus 4 and a y minus 2. So we have to have both of them. When we look to this fraction, it just needs a y minus 4. Well, guess what? There's already a y minus 4 there, so we don't have to put another one. Likewise here, this denominator is just a y minus 2, so we already have a y minus 2, so we don't need to put an extra one. That's what I mean by overlapping. Every denominator is represented, okay? This denominator here is shown by both. This denominator here is represented by the first factor, and this denominator here is represented by the second factor. Let me give you a couple more examples that shows some of the more common mistakes that I see. Here's one, I've already factored it for you. We have an x plus 4 and x minus 3, but this denominator has two x minus 3's. So when do we need just one x minus 3? When do we need two? Remember, every denominator has to be represented completely. So in this case, we're going to have an x plus 4 from the first one, an x minus 3 from the second one. Then when we look to the last one here, we say, well, it has an x minus 3. Well, the first one already had an x minus 3. But it has a second x minus 3. Therefore, we need a second x minus 3. An easy way to check is to see if you can kind of cover up some of the factors to see if you could see all of the denominators. If I cover up the last two, there's my x minus 4 from my first one. If I cover up kind of the outside ones there if I wanted to, there's my x minus 3 from my second one right there. And if I cover up the first one, I can see my last denominator, both x minus 3's. Okay? Also, with the second example here, a common mistake is people go, oh, well, there's an n minus 5 and it already has an n in it, so I don't need this extra n. Good thinking, but this n minus 5 is a factor within itself. N minus 5 is a binomial factor. It's all or nothing. This factor here is a monomial factor. It's a single n. They're two different factors, so both has to be represented. What may help you is to go ahead and put parentheses around any binomial factor that's already simplified. If you can't go any further, just go ahead and put parentheses around it, and that will remind you it's all or nothing, and everything has to be represented. So the LCD here will include both the monomial n and the binomial n minus 5. Oop. So a few things that I want to recall before we do a huge example with the solving. Fractions represent division. Remember, your goal is to get x by itself. So if you've got a fraction, in order to get the x's out of the denominator, you have to undo that fraction somehow. You have to get rid of the denominators. So how do we undo division? Multiplication. So that's going to be kind of your thought process when you're working through these and you get nervous on a test and you go, oh, I'm frozen, what do? You go, I need to get x by itself. I can't get x equals a number as long as that x is in the denominator. It's in the bottom of a fraction. Fraction represents division. Multiplication undoes that division. Think of what gets rid of that obstacle. Last but not least, you cannot divide by 0. That's a long-standing rule. It doesn't change whether you're dealing with numbers in your fractions or variables in your fractions. You cannot divide by 0. So we can't have 0 as a denominator. That's going to come in handy when we must check our answers, okay? Okay, so we're going to do the rational example here on the notepad instead of on the slides, because it does take up a little bit more room. So we'll do the steps right here. Factor the denominators. Okay, we'll do a little shorthand here. Now, if you'll notice these last two fractions here, the denominators cannot be factored any further. So sometimes it's helpful to go ahead and put parentheses around it. That way you know you're not going to do anything else with them just yet. However, this trinomial here in the first fraction can be factored into y minus 4, y minus 2. Now, what are we going to do with that? That's going to help us find our LCD that we already talked about. So our LCD here is going to be y minus 4, y minus 2. So if our goal is to get the y by itself, we have fractions, we found the LCD, what are we going to do with that LCD? Well, normally if we're just adding and subtracting fractions, we want the denominators to be the same so we can add or subtract. So we multiply top and bottom. We do one of these things. The problem is we have an equal sign, okay? Our goal is not to add or combine the fractions. Our goal really is to get rid of the fractions. We don't want the variables down here, so we want to undo the fractions. So think fraction means division, that's the operation. Multiplication undoes the division. So we're going to take this LCD and we're going to multiply. So multiply by the LCD. So if we rewrite the first, we have y squared minus y minus 2 over, I'm going to use the factored form on the bottom, y minus 4, y minus 2. And I'm going to multiply that by our LCD, y minus 4, y minus 2. Then I'm going to take the second part, the minus 5 over y minus 4. Multiply that by our LCD. Notice the LCD is going in the numerator, in the top, because it's understood to be over 1. We're not doing the top and bottom thing. We're just multiplying to reduce the fractions. And then our last piece. Okay. Now, how does this help us? Well, first of all, let me highlight this just to illustrate, yes, everybody got the LCD there. Well, now we can reduce and divide out these denominators. Yay! Which is kind of our goal right now. We don't want these down here. So the y minus 4s divide out to 1, y minus 2s divide out. In the second one, the y minus 4s divide out. In the third one, the y's minus 2 divide out. And so those guys are left. The 3 and the y minus 4 is left. And this guy here is left. So let's rewrite it. We have y squared minus y minus 2 minus 5. We still have the y minus 2 equals 3 times y minus 4. So here, in step 4, we reduced. So reduce. And we're also going to simplify. So reduce and simplify. It looks like we now have a quadratic equation. So if all of this other here is kind of getting you visually disconcerted, if this is getting a little bit overwhelming, remember you can take a blank piece of paper and cover what you've already worked with so you only see what's left. Okay, give your eyes a little bit of a break. So here we can simplify the left-hand side and the right-hand side. Here on the left, we can distribute y squared minus y minus 2 minus 5y plus 10. We can also distribute here on the right, 3y minus 12. The left-hand side, we have some common terms here, some like terms that we can combine. The negative y and the negative 5y combine. So we have y squared minus 6y. And then the negative 2 plus 10 gives us a plus 8. And the 3y minus 12. Hey. So don't give yourself a headache. I'm going to scroll this down for a second. I'll try to do it slowly. Step 5 is going to be solve. Now remember, you may have a linear equation, you may have a quadratic equation. Right now, we have a quadratic equation, which means we need to set it equal to 0. So let's go ahead and do that in one step here. We're going to subtract 3y from both sides. And let's go ahead and add 12 to both sides. So that will give us y squared minus 9y plus 20 equals 0. So we have y minus 4y minus 5 equals 0, and then set each of those linear factors equal to 0 and solve. So we can't forget how to solve linear equations or how to solve quadratic equations. They're going to continue to show up. We have a caution here. Our original equation was rational, so we had a fraction, right? What are we not allowed to have in the denominator of a fraction? 0. Good. We can't divide by 0. It's not allowed. Just like with square roots, we can't take the square root of a negative number. It's not allowed in the real number system. So whenever you have a restriction, we call it a restricted domain, whenever you have a restriction in your original equation, you always must check your answer to be sure that it's allowed. Okay? So here you can check your result in the denominator. Remember, we can't have a number over 0. Okay? If we come back up here into the original equation, We would be in trouble if we had a 4, because 4 minus 4 would give us a 0 here, or if we had a 2, because it would give us a 0 here. Same thing here. 4 or 2 would give us a 0 in the denominators. So as long as we do not have answers of 4 or 2, we're good. But remember what we had. So we scroll down again. I'll go slowly. Don't want you to get a headache. One of our answers was a 4. That doesn't mean none of them work. It just means we have to not use the 4. So our only solution would be y equals 5. So it's possible you can have 2 solutions. It's possible you only have 1. It's possible you have none. Okay? But just double check, make sure it works. Whenever your original equation has restrictions, like fractions or square roots or logarithms, which you'll learn later, you must check your answer. It's always good to check it anyway, just to see how you did, but you must do it when you have one with restrictions, with a restricted domain. Okay, so here's an example that I want you to try on your own. So when you're ready, pause the video, go ahead and try it, and then when you're ready to see how you did and look at the results, then hit play. But try it first. Are you ready? Ready to see how you did? Okay. We need to find the LCD. And in order to do that, we need to factor all of the denominators. This first denominator is already factored. Second denominator, it's as simplified as it can go. Now the trinomial factors into x minus 6, x plus 3. So our LCD, we have to have the first denominator represented. So we have to have an x minus 6. With the second fraction, we have to have that denominator represented of x plus 3. And then luckily, this last fraction has both the x minus 6 and x plus 3, and they're both already represented. Now we need to multiply everybody by that LCD in order to reduce and get rid of those denominators. So we have 5 over x minus 6 times x minus 6x plus 3. Plus 4 over x plus 3 times x minus 6x plus 3 equaling 4x plus 1 over, and I'll go ahead and do the factored form so we can reduce a little easier, times x minus 6x plus 3. So remember, everybody got the LCD, equal opportunity mathematician. And then we divide out anything that they have in common. Let's see what is left. On the first one, we have a 5 and the binomial x plus 3. Second, we have the 4 and the binomial x minus 6. And the end of the equal sign, the 4x plus 1. So let's go ahead and simplify. If we distribute, we get 5x plus 15. Distribute the 4, we get 4x minus 24, and then 4x plus 1. Let's go ahead and simplify the left-hand side. We have a 5x and a 4x that we can combine, which gives us a 9x. And then we've got the 15 and the minus 24, which gives us a negative 9, equals 4x plus 1. If we subtract 4x from both sides, then we will get 5x minus 9 equals 1. Add the 9 to both sides, we get 5x equals 10. Divide both sides by 5, and we get x equals 2. Only one solution here, and as we check back, here in the original, if I plug in 2 anywhere in the denominators, I'm not going to get 0 in the denominator. So we're looking good. So how do you feel about solving rational equations? Hopefully a little bit better than when you started. If you got it wrong, don't stress, but go back and figure out where your mistake was, correct it, and get help. Ask your friends, watch more videos, watch this again if you need to. Don't let your pride keep you from passing. You're not alone in this, okay? So have fun. We'll see you soon. Hi, welcome back. Today we're going to take a look at solving radical and power equations. if you're in Algebra 1 or a beginning algebra class, you may only be working with square root radicals, and that's fine. This segment will still help you a great deal. So what do I need to know in order to solve these types of equations? Well, let's first determine what they look like. A radical equation will have a radical in it, like a square root or cubed root or fourth root, and you may see more than one. This little n here in the crook of the radical is called the index. If you don't see that little number, it's understood to be 2 for a square root. A power function could be a cube or a quadratic, an x squared, an x cubed, x to the fourth. The only difference is you don't have other x terms. Like you're not going to have an x cubed and an x squared or an x squared and an x. You have one term with that variable power in it, and they're easier to solve. Also, we need to see how radical and powers undo each other. Let's first see how they're inverses, how they undo each other. If you have an x cubed, in order to undo that cube, to get rid of that cube, we have to use its inverse. So we would take the cubed root. Those two 3's undo each other, and we would be left with just the x underneath. Likewise, if you start with a square root, let's say the square root of x, and again, remember, because it's a square root, that's an understood 2. To get rid of that square root, we would square it. These two 2's here, the square root and the square, are inverses. They will undo each other, and you're left with just the x underneath. And we have to write assuming x is greater than or equal to 0, especially for the beginning algebra students, mainly because we can't take a square root or any even index root of a negative number, because even a negative times a negative will always equal a positive. As long as they're paired up in evens, you're always going to end up with a positive number. With cubes, fifth roots, seven roots, any odd index radical, we can do negatives. So just a reminder there. And last but not least, let's take a look at this one. We have the fifth root of the binomial x minus 3 taken to the fifth power. So again, the power and the root will undo each other as long as the number is the same. And we're left with what's underneath the radical called the radicand, x minus 3. So let's do a couple of examples. Suppose we have this radical equation here. Now remember, the key to solving algebraic equations is to remember your final goal. Take your original equation, undo any of the obstacles that are in your way so you can whittle it down to x equals a number. Well, right now, my biggest obstacle is that radical. So we're going to get the radical alone by subtracting that 1 from both sides. Now we have the radical by itself. It's an understood 2 here. It's a square root. So to undo the square root, we're going to square it. But remember, if we do something to the left side of an equation, we have to do it to the right. So on this left side, the square and the square root undo each other, and we're left with just the radicand underneath, 7 minus x. 4 squared gives us 16. Now we have a linear equation, and you've been solving linear equations for a long time now. So we're going to get this x by itself by subtracting 7 from both sides. Then we get negative x equals 9, and then we're going to divide both sides by that understood negative 1 there, and we get x equals negative 9. But don't celebrate just yet. We have to check our answer. Now, the reason we have to check it, it's always a good idea anyway, just to be sure that you got it right. It helps leaving the test knowing whether or not you got it right, correct? But anytime you have an equation where your original problem has restrictions, if you're in Algebra 2 or intermediate algebra, we call it domain, a restricted domain. But anytime you have a restriction, like in a rational equation where there's fractions, remember you can't have 0 in the bottom of a fraction. That's a restriction. So you have to check it, make sure your answer didn't give you a 0 in the bottom. In the real number system, we can't take a square root of a negative number. So we have to double check and make sure that our result did not give us a negative number under here. We have to make sure it works. So we're going to plug in our result of negative 9 in for x. Remember, a negative times a negative gives us a positive. So we get the square root of 16 plus 1 equals 5, and the square root of 16 is 4. So it works. 4 plus 1 is 5. So don't forget to check your answers. Now, with power equations, I can tell this cubic here is a power equation because I only see one term with the x cubed. If you combined all your like terms and you only had one of those, then it's a power function. So again, we're going to whittle it down, undoing everything to get x by itself. So let's subtract 4 from both sides. We get 2x cubed equals negative 20. Now we need to get rid of the 2. It's being multiplied, so we're going to divide both sides by 2, and we're left with x cubed equals negative 10. Now we need to get rid of the cube. Remember, the inverse of a power, that cube, is going to be the radical, the cubed root. But if we take the cubed root of the left, we're going to have to take the cubed root of the right. So this cubed root and this cube undo each other, and we're left with x. And here, when you take a cubed root of a negative number, which means is valid, okay, remember that that's valid, as long as the index is odd, we can take out that negative and just leave it the cubed root of 10, which does not reduce. So that would be our final answer. So now I want you to try. We've got a radical equation and a power equation. So go ahead and pause the video, give them both a shot, and when you're ready to see the results, hit play. Pause it. All right, here we go. This one is radical because you see the cubed root that we have here. So remember, in order to undo it, we need to isolate it. We need to get it by itself. So since this is 2 times that radical, just like if it was 2x, it's understood to be 2 times x, 2 in front of the radical, 2 times the radical. So we're going to undo that using division. So divide both sides by 2. So these 2 divide out to 1. So we're left with just the cubed root of x plus 5 equaling 3. And the inverse of a radical is its power. So look at the index. We've got a cubed root. So we're going to take the power of 3 to both sides. And these 3's undo each other, the radical and the powers. And we're left with x plus 5 equals 27. And then subtract 5 from both sides. It's a nice linear equation. And we get x equals 22. Since we're dealing with a cubed root and not a square root, we don't have to check our answer. Because you can take a cubed root of a negative number, but you can't take a square root of a negative number. So 22 in there will be just fine. This one is a power function. We see the variable taken to a power, an exponent, but there's no other variables. You don't see an x cubed or an x or anything like that. So we can isolate this x to the 5th by adding 13 to both sides. We have 4x to the 5th equaling 20. And then dividing both sides by 4. They divide out to 1. Leaving us with x to the 5th equals 5. And remember, now to undo this power of 5, we're going to use its inverse, which is the radical. So now we're going to use the 5th root of both sides. And so the 5's reduce, and we're left with x equals. Now, I often see people putting in a 1 here. So be careful. Remember, powers and roots, radicals, are talking about how many times you multiply something by itself, not adding. 1 added to itself 5 times is 5, but 1 multiplied by itself 5 times is still 1. 1 times 1 times 1 times 1 times 1 is 1, not 5. So this is as reduced as it's going to get. There you go. So how did you do? Not that bad, right? Once you determine all of the pairings that undo your obstacles as you whittle down those equations, solving algebraic equations really isn't that bad. Just know what your pairings are, know what your goal is. So if you have any questions on the power functions or the radical functions, feel free to watch the video again. Find other videos online. There's plenty of them out there on YouTube or other places. Also, check with your teacher, check with a tutor, check with your friends. There are a lot of resources. So don't let your pride keep you from passing. Believe me, you are not alone. So be sure and ask questions. Okay? We'll see you again next time. Welcome back. Now we're going to take a look at solving quadratic equations using the quadratic formula. And again, quadratic equation is a polynomial equation where your highest exponent is 2. Now, what do you need to know in order to solve using the quadratic formula? First of all, you need to know the quadratic formula. It's x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In a minute, I'll explain to you where all of those little a, b's, and c's come from. We also need to know how to simplify square roots and how to reduce fractions. So if you've got all of these in your toolbox, then you'll be able to solve using the quadratic formula. So your first step, know the formula. You can make up a story about what B and A and C stand for. You can sing it to Pop Goes the Weasel, which I'm not going to attempt right now, but it's public domain, so I could. But you could sing it to, x equals opposite b plus or minus square root b squared minus 4ac all over 2a. And I just did it anyway, didn't I? Okay, sounds silly, but it works. But I think one of the best methods of memorizing it is every time you use it for a problem, you rewrite it. Rewrite it and say it out loud to yourself. 1, because it gives you a physical of writing it. 2, it gives you a visual. You're going to see it over and over again. And 3, it's going to give you an auditory because you're going to say it over and over again. The more senses that you use to try to learn something and memorize something, the more likely your brain is going to access it when you get nervous, like when you're trying to take a test, okay? So trust me, it takes an extra, 6 seconds per problem to rewrite it. It's going to take maybe a little bit of extra paper, but it's a lot faster, easier, and cheaper than taking the class over again, right? Okay? So just trust me on this. You've got to know the formula. Now, where do all of those little variables, the a, b's, and c's, come from? So the variables in the formula come from the coefficients in the quadratic equation. So if you have the quadratic equation set equal to 0, and it's in proper format, descending powers, x squared, x constant, all of the numbers here are your a, b, and c in alphabetical order. Pretty cool, huh? Now, the nice thing about the quadratic formula, I know we've already learned how to solve quadratics using factoring, but sometimes those polynomials aren't factorable. The quadratic formula always works. Doesn't matter if it's factorable or not. The quadratic formula always works, so it's nice to know. So the second step after you've learned the formula is to set the equation equal to 0 and plug in. So let's look at this example. 3x squared minus 2x minus 1 equals 0. It's in standard format, equal to 0, so our first coefficient here is going to be our a, which is 3. The second one's going to be our b, which is negative 2, and the last one is our c, which is negative 1. So let's remind ourselves of what the quadratic formula is, and now let's plug in. We've plugged in the b, which is negative 2. Notice here it's the opposite. Somebody will say negative b, but really it's the opposite of whatever b is. So if our b started out as a negative 2, it's going to become a positive 2. And if you want to go straight to the positive 2, that's fine. I just wanted you to see why it changes. And then we also had the b put in there. Here are our a's for the 3, and then the c, which is negative 1. Once you have everything plugged in, our third step is to reduce the fraction. So we just take everything and reduce it. The minus and negative 2 there is going to become a positive 2. Negative 2 squared is a positive 4. Here, some people have trouble with the signs. Remember that that minus 4, that little hash mark there, also plays double duty. It also means negative 4. So when we're multiplying, negative 4 times a positive 3 is a negative 12. Negative 12 times a negative 1 gives us a positive 12. Negative times a negative is a positive, which is why we have a plus here. Now, this 4 plus 12 can be combined to give us 16. The nice thing here is 16 is a perfect square. So we have plus or minus this, so we have two different numbers that we're going to be looking at. The first one is the x plus 4. Again, the 4 is the square root of 16. And now that gives us 6 over 6, which is 1. Our second one has the minus sign, 2 minus 4, which would give us negative 2 over 6, which reduces to a negative 1/3. So you need to know the formula, you need to be able to plug in, and you need to be able to reduce. Okay? Now, there are three possible types of solutions when you're dealing with a quadratic formula. One, you can come up with rational solutions. If you come up with rational solutions, you could have factored it, which is fine. You don't have to unless the teacher requests it. If it just says solve, you can use whatever method you want. So x equals 1, x equals a negative 1/2. But if that square root is not a perfect square, then the square root is going to be left in your answer. This is called an irrational answer because you have irrational numbers in here. It's also possible to get a negative underneath that square root, which means you have no real solution. So if you're in Algebra 1, you may not be covering complex numbers, which involves imaginary numbers or the I. So you're just going to say no real solution because you cannot take the square root of a negative number in the real number system. If you're in Algebra 2 and you've covered complex numbers with the I's, then you can ask your teacher, do you want it in the real number system or do you want me to put the I? So it depends on which class you're in as to how you would show those results there. Number of solutions, we'll just go over this real quick. It depends on what's underneath that square root, but it's all based on your, based on the graph. You're looking for your x-intercepts. So you can either have 2 solutions, 1 solution, or no solution. No real solution because there are no x-intercepts. This is where your complex answers would come in. Okay, so now I want you to try. Here are 2 examples. Go ahead and pause the video, give it a shot using the quadratic formula, and then when you're ready to go over your answers, go ahead and hit play. Okay, are you ready? Let's take a look at the I feel like a cheerleader. Okay, quadratic formula. All right, don't know why I did that. So here we've got a quadratic equation. I went ahead and wrote down the quadratic formula. Remember, you want to have that physical memory, the touch memory, kinesthetic, write it down. It's not set equal to 0, so you may want to kind of make note of that. We need to change it. Set equal to 0, so let's subtract 3 from both sides. So we get 5x squared minus 6x minus 3 equals 0. Now here is our a, b, and c. So not only do you want to write down the quadratic formula, but also say it out loud when you write it down and when you fill it in. So we've got the opposite of b, so the opposite of negative 6, plus or minus the square root of our b squared minus 4 times our a times our c. Extend that radical. Everything over 2 times our a. And now we can simplify. Opposite of negative 6 is a positive 6. Plus or minus the square root, negative 6 squared is 36. Then we have a negative 4 times 5 is a negative 20. Negative 20 times a negative 3 is a positive 60. So be careful with your signs. 2 times 5 gives us 10. So we have x equals 6 plus or minus the square root of 96 all over 10, but we're not done yet. Okay, we're going to keep going. The reason is a couple of things. The square root of 96, even though it's not a perfect square, it's not simplified completely. There are some factors in there that are perfect squares that we can take out. Second, we need to reduce this fraction if we can. What some people do, unfortunately, is they reduce the 6 and the 10 here, and you can't do that. Remember, you still have terms up here. You've got addition and subtraction. You cannot reduce with addition and subtraction. Everything has to be multiplied, or at least every factor in there has to be divided by the same number. So let's go ahead and reduce the square root of 96. Let's see, so we have 6 plus or minus, is that 6 times 16, I think? So 4 radical 6, all divided by 10. So notice you could divide out a 2 here from the 6 and the 4 and then reduce the 2 and the 10. But a quicker way is to reduce every piece by the same number, which is basically what dividing out that 2 means. So 6 divided by 2 is 3, 4 divided by 2 is 2, 10 divided by 2 is 5. So that gives us 3 plus or minus 2 square root of 6 divided by 5. Now, just to be sure that you understand that this plus or minus means that we have two numbers here. 3 plus 2 square root of 6 over 5 and 3 minus 2 square root of 6 over 5. So your teacher may request that you write both of them out. 3 minus 2 square root of 6, all divided by 5, and 3 plus 2 divided by 6, all divided by 5. And there are your two solutions. And if your teacher lets you leave it in this form, bully for you, not a big deal. But a lot of teachers want to see both of it just to make sure that you understand that there's two solutions. Okay, all right, let's take a look at the next one. Again, quadratic formula, already written. Quadratic equation, already set equal to 0. So we can label our A, B, and C. A, B. Now notice the B here is not the X. Okay, it's the -1 in front of the X and your C. So if you need to write that 1 in there, just so you can visualize it, go for it. And now we plug it in. So X equals the opposite of B plus or minus square root B squared minus 4AC all over 2A. Okay, so now let's reduce. Sometimes you gotta do it just for yourself. The opposite of -1 is 1. Plus or minus the square root of -1 squared is 1. -4 times 6, -24. -24 times -2 is a positive 48. So double check your signs. See how you're doing so far. So that gives us x equals 1 plus or minus the square root of 49 over 12. I'm going to continue it on over here. What's the nice thing about the square root of 49? It's a perfect square. So we have 1 plus or minus 7 divided by 12. But remember, this plus or minus gives us two different results. Even though some teachers allow you to leave your answers with the plus or minus if you've got the radical there, okay? In other words, it's an irrational answer. If you come up with a rational answer, in other words, you have a perfect square, reduce it to the numbers that you're familiar with. Go ahead and give those two results. I'll just put two little arrows here. So we have x equals 1 minus 7 over 12, which is a -6/12, which reduces to a -1/2 is one of our results. Then we have x equals 1 plus 7 over 12, which is 8/12, which reduces to 2/3. So there are our two solutions. So don't forget, watch your signs, be sure you know the formula, be sure you reduce any radicals that you can, and reduce your fractions as far as you can. So how did you do? Take a look and see where you made your mistakes. Was it in plugging it in? Did you set it equal to 0? Were you able to reduce it okay? There are different places that people kind of mess up and they need to work on. So just find what it is and fix it. Yeah, easier said than done, I know. But go to your teacher and ask for help. So remember, Set it equal to 0 before you use the formula. You can have between 0 and 2 solutions. Watch out for that negative number underneath the square root, and reduce your final answer if possible. Okay, well, thanks for watching. I hope you guys enjoyed it, or at least it was better than, I don't know, drinking your own bathwater. So, don't forget, you have a lot of resources, videos, teachers, friends, tutors. Go ask for help. Don't let your pride keep you from passing. You're not alone in this, okay? Okay, so we'll see you guys again soon. Hi, welcome back. Today we're going to take a look at solving absolute values, equations, and inequalities. One method for all of them, which is very nice. So, what do I need to know in order to solve absolute value equations? First of all, definition of absolute value, how to distribute a -1, probably like that one, and also how to solve linear equations and inequalities. So, absolute value is the distance from 0 on the number line. A lot of people think, well, absolute value means it's always positive. Well, that's true, but this is why. And this is very important to remember because it's going to help you to remember how to approach these problems and how to set up your solutions. Distance from 0 on the number line. You never see a negative number on like a tape measure or a ruler, or if you drive your car backwards, numbers aren't going to come down off the odometer. It's still positive. Distance is always positive. So let's take a look at this example. If we've got the absolute value of -3, notice how far away -3 is from 0 on the number line. It is exactly 3 units away. That's why the absolute value of -3 is 3. Likewise, the absolute value of +3. Well, +3 is 3 units away from 0. So the absolute value of 3 is also 3. So that's kind of the key here, is that there's always a positive and a negative number that have the same absolute value. Opposites have the same absolute value. Absolute value of 4 is 4. Absolute value of -4 is 4. Here's where it's going to help you when you solve. Take a look on the inside of the absolute value. One of them is always as is. Let's say the positive version. The other one, the inside is always the opposite of that distance. Okay? One is as is, or positive. The other one is the opposite. Same thing here. Absolute value of 10 is 10. What other number has an absolute value of 10? Good. -10, it's opposite. So the inside as is, or the inside has its opposite. Sorry, I'm fighting a cold. Bear with me here. So a number and its opposite always have the same absolute value, but what if the inside is a variable? It's the same concept. If the absolute value of x is 3, then we have two possibilities. Either the inside is as is, in other words, x just equals 3, or the inside is its opposite. The opposite of x is 3. And when you divide both sides by that understood -1, we get x equals -3. I already know what you're thinking. Well, I know absolute value is 3. It has to be either 3 or -3. Why do I have to go through all of this as is opposites? The reason is all the problems aren't going to be this basic with just one single variable. You might have a 2x plus 7 or a 1/3 x minus 3/5. It's going to get a little bit more involved, but the concept is the same. One method, all problems, doesn't matter how difficult it is, doesn't even matter if it's an equation or an inequality. They're all going to be worked the same, okay? Trust your Aunt Lainey on this. So let's take an example here where it's a little bit more involved. We do have an absolute value, and remember your goal is to get the x by itself. You have to whittle it down where x equals a number, same as all the other types of equations. So the first thing we want to do is get rid of our obstacles, which right now is our absolute value. So we're going to get that guy alone by adding 2 to both sides. Now we're going to set up our two different solutions. One of them, the inside is as is. So imagine just dropping. Great grammar. Where did that come from? Just imagine dropping your absolute value and you have this first equation. Be careful. If this is all you put, I doubt if your teacher gives you partial credit, I doubt you'll get any, okay? The reason is If this is all you do, then you're saying, the absolute value doesn't mean anything. Just get rid of it, okay? So you have to remember distance from 0. There's always two numbers that have a distance from 0. One's on the positive side, one's on the negative side. So you're showing the inside as is or positive. Now you have to show the opposite possible answer. So we're going to distribute a -1 to everybody that was inside that absolute value. Don't just change the sign here. Don't just make it a -3. You have to change all of their signs, okay? So now let's solve. Over here, if we subtracted x from both sides to get a 6x, subtract 2 from both sides, got our 1. Solve for our x, we get a 1/6. Likewise over here, let's distribute that -1, and we get a -x minus 3. Combine our x's and our constants, divide both sides by 8. So here's where solving linear equations comes in handy. Be sure you have that mastered. The nice thing is, it also works with inequalities. You don't have to learn a different method. So consider this. Absolute value of -y minus 2 less than or equal to 1. Set up your two possible solutions. The inside as is. -y minus 2 less than or equal to 1. I haven't changed anything yet. Second possibility, you got to look at your opposite of the inside. So we're going to distribute a -1 to everybody that was inside that absolute value. And now we solve. If you add 2 to both sides here, you'll get a 3. But recall, when solving inequalities, whenever you multiply or divide by a negative number, what has to happen to that inequality sign? Exactly, you have to switch it. So watch this screen. I'm going to divide by -1, but notice what happens to my inequality. It switched. Now it's greater than or equal to. Technically, you need to do it the second you divide by -1. Otherwise, that step was wrong. So be sure that you switch it. And we get y is greater than or equal to -3. Then we solve this side. Distribute the -1, we get a positive y plus 2 less than or equal to 1. So y is less than or equal to -1. Now let's take a look how we can put these two together. Both of these have to be satisfied because we've got a less than 1. So on the left, we have y greater than or equal to -3. So this is what the graphing on the number line would look for just this portion of the solution. You have the bracket because it's or equals to, it's included. If we looked at this solution, y less than or equal to -1, we have the bracket at -1, but it includes all the solutions to the left. Well, if it has to satisfy both, where do these two overlap? Right there in the middle, between -3 and -1. So our answer in interval notation is between -3 and -1. So now you try. Here are a few examples, practice problems. Go ahead and try it. Pause the video, give it a shot, and then when you're ready to kind of scan over them and see how you did, hit play again. All right, let's take a look. On the first one, we have an absolute value of x plus 3 greater than or equal to 7. So remember, we have our two solutions. One will be written as is. Interesting, nice little extra piece there. So we would have x plus 3 greater than or equal to 7. And then our second solution, we're going to use the opposite based on the definition. So it's the opposite of everything on the inside is also greater than or equal to 7. And this way we don't have to worry about, wait, do we switch it on the second one where it's also less than? Do we switch the signs? What do we do? Everything falls out old school. So under the as is, if we subtract 3 from both sides, we get x greater than or equal to 4. The opposite, we're going to distribute the -1, so we get a -x minus 3 greater than or equal to 7. Add 3 to both sides, we get the opposite of x greater than or equal to 7. But remember, we need to divide both sides by this -1 to get the x by itself. And when you divide, that inequality sign has to change. Okay, so it's no longer greater than, it's now less than. So x is less than or equal to -7. Let's draw a little number line over here, actually. Let's make this 0, 4, and then out here a little bit more, a -7. So for the x, for this part, where x is greater than or equal to 4, we would have the bracket, and it goes off to the right. And for the part where x is less than or equal to -7, everybody less than -7 is there to the left. Thus, we're using the brackets to represent the or equals to part. So this left portion here, less than or equal to -7, would be represented everybody from -infinity to -7, where -7 is included. In union with, in other words, also, or, we can use everybody from 4 all the way out to positive infinity. And remember, your infinities, if you're using interval notation, your infinities use the parentheses because it's not an actual endpoint that you would use. Infinity is not a number you can plug in. 4 is a number we can plug in, and it's one of our solutions because it's greater than or equals to 4. So we have to use the bracket. Okay, on B, same thing. We still have the absolute value, but we need to get it by itself first before we do the as is and the opposite. So let's go ahead and divide both sides by 2. So these guys divide out, and we're left with the absolute value of x plus 5 is less than 6. Okay, so we've got the as is, which would be the x plus 5 less than 6. And we also have the opposite. So we take the opposite of the inside. Everybody on the inside is less than 6. So those would be our 2. So let's work the as is. Subtracting 5 from both sides, we get x less than 1. Let's go ahead and distribute the -1 to get -x minus 5 less than 6. Add 5 to both sides, and we get -x less than 11. And again, if you divide both sides by that -1, you have to switch the inequality to greater than. So that's going to give us an x greater than -11. So let's go ahead and do a number line over here so we can visualize our results. I'll put my 0 and my 1 here, -11 way over here. And again, this isn't to scale, this is just to give us a visual to help us with our answers here. So with the as-is result, we have x is less than 1, but 1's not included, so we would use parentheses. It would go that direction. And x greater than -11, -11's not included, and all the numbers greater than will go in that direction. Well, where do they overlap? That would be our solution. So everything in between -11, not including -11, and 1, not including 1, would be our result there in interval notation. So let's do the third one, where I believe it was an equation, which it is, yay. Still need to get the absolute value by itself, so let's add 7 to both sides and get equals 6, and then do our two solutions. So the first one is as is, 3x plus 2 equals 6, and the second one would be an opposite, where we have the opposite of the entire 3x plus 2 equals 6, and we distribute the negative. For the as-is, if we subtract 2 from both sides, we would get 3x equals 4, and divide both sides by 3. We get 4/3, or 1 1/3, as one of our solutions. And on the opposite, if we add 2 to both sides, we would get a -3x equals 8, and then divide both sides by -3. We get a -8/3, which is a -2 2/3. Notice we're not putting it on the number line here. We're not worried about interval notation because we don't have inequalities. You're not looking for a stream of numbers, an interval of numbers at work. we have an equal sign. So we just want to know those particular values. So how did you do? I don't want you to get too frustrated. Hopefully you've got some confidence now. More than I do with this sore throat. So if you do have any questions or you made a few mistakes, take a look back and see where they are. Usually they're easily corrected. Remember, it feels like if you don't understand, it's a Grand Canyon between you and getting it, when oftentimes it's just really a small crack in the sidewalk. So figure out, what is that crack? What do you have to overcome to get to this? Ask your teacher. And if your teacher and you don't mix, don't let that keep you. Don't let that be an excuse. Find somebody else. Find a tutor, find another teacher, find a friend. There's websites, there's more videos. You've got plenty of resources out there. So don't let your pride keep you from passing. Ask questions. I'll see you again next time. Hi. Today we're going to take a look at solving logarithmic equations. I know you guys have been looking so forward to this. You've heard about logarithms for a long time. But today we're just going to take a look at the basics, the nitty-gritty. So first of all, you've got a log base a of x equals c. We need to keep in mind that your base here has to be greater than 0, and it cannot equal 1. So you can have positive fractions and any positive numbers greater than 1, which also means that this number here is going to have to be positive. And that's based on the definition, which I'll show you here in a second. So what do I need to know? First of all, the definition of a logarithm. I want you to think exponents. Logarithms represent exponents. Now let me show you how. If we have the logarithm of base a of x equals c, notice I'm saying base a. Think of base of an exponent. If we take that base of a, we can take it to the power of c. Remember, logarithms represent exponents. So a to the power of c should equal what you're taking the log of, which in this case is x. So we're able to rewrite this logarithm equation as an exponent or possibly an exponential. A to the c equals x. This is going to help us to undo the logarithm using the definition. Also, if you see a logarithm and you do not see a base, it's understood to be base 10 since we work in the base 10 number system. And also, this is called a natural log. It's still a logarithm, but it's understood to have a base of e. So anytime you have an equation with e, you're going to use the natural log. You also need to know the exponent rules with like bases. When do you add exponents? When do you subtract? And also how to solve all the previous types of equations that we've done. Linear, quadratic, radicals, rationals. It depends on how your logarithm reduces. So let's review how the exponent properties that we've learned in the past affect the logarithm properties. Remember, if you have a like base and you're multiplying, we add exponents. So with logarithms, since they represent exponents, if you are multiplying with a single log, you can rewrite that as adding. Remember, like adding two exponents. Likewise, if you have two logarithms and you want to write it as a single log, which is what we're going to be doing today, you can write it as a single logarithm, but instead of addition, you now have multiplication. So a single log of multiplication into two logs of addition, or two logs of addition into a single log of multiplication. Same thing works with division. When you divide like bases, we subtract exponents. So guess what we're going to do with a logarithm if we're taking the log of a fraction? Exactly. Logarithm of a fraction, which means division, can be rewritten as two logarithms using subtraction. Or if you have two logarithms that are being subtracted, we can rewrite it as a single logarithm in division. So if you remember the exponent properties here, and the fact that logarithms represent exponents, that's going to help you to remember this relationship, okay? And we're going to be going this way a lot today. Two logarithms into one, because remember we're trying to solve, which means we need to reduce that equation, whittle it down. The very last one, this one actually you're going to use in the next segment when we're solving exponentials, but it's very important, so I'm going to have you start this one. If you have a base and you're taking a power to a power, we multiply exponents. So if you have a logarithm that represents an exponent and it's also being taken to a power, we are allowed to rewrite it with the exponent in front and then have the logarithm base a of m here. So we are able to write it as multiplication, in essence, of two exponents, the exponent you had here and the logarithm that represents an exponent. So if you remember to move any exponents to the front, this is going to help you when we start solving exponential equations in the next segment. Let's take a look at this example. Log base 3 of x plus log base 3 of the binomial x plus 8 equals 2. Again, your goal is to whittle down the equation, get rid of any obstacles so we can get x equals a number. Well, the logarithm is definitely an obstacle, and we've got two of them. So remember, if they represent exponents, when do we add exponents? When we're multiplying like bases. So we can rewrite this as a single logarithm, okay, rewrite as a single logarithm, and then multiply the items that we were taking the logarithm of. One thing I want to point out, what a lot of people want to do here, is they want to distribute this log, okay, and it's very common. You see something in front of parentheses, oh, I know how to distribute, I want to do it. You have to refrain from doing that. The reason is, log by itself is meaningless, okay? It's not a number. So you can't multiply it or distribute it like it's a number. I couldn't divide both sides by log of 3 to get rid of it because it's not a number. It's a function. You're taking the logarithm of something. It's always of something. So it has to have a number attached to it at all times. So you can't distribute, but you can combine into a single logarithm using the multiplication and addition properties. So now that we have it here, let's go ahead and simplify what's inside, x squared plus 8x. But we still have that logarithm that we don't want. So we can use the definition to, in essence, undo that logarithm. So use the definition. We have a base 3 taken to the power of 2. That should equal what we're taking the log of. So let's rewrite it. 3 to the power of 2 equals the x squared plus 8x. Now we have a quadratic. So we can use either the quadratic formula or we can factor it. It happens to be factorable. So if we factor the right-hand side, we get x plus 9 times x minus 1. Set both of these factors equal to 0, and we would get x equals negative 9 and x equals 1. Don't party just yet. Remember, anytime we have an equation that has a restriction, a restricted domain, we have to check our answers. Logarithms, the bases have to be positive, which means any exponent I take it to is going to give me a positive number. So we can't take the logarithm of a negative number, which means this guy doesn't work. So check it, can't take the log of a negative number, so that x equals negative 9 doesn't work. So our only solution is x equals 1. And we can plug that into the original to make sure it does work. So now I want you to try. Here are 3 different equations to solve. Remember what the understood base is here. Okay, base of e. Go ahead and pause the video, give it a shot. Remember, before you're right, you have to be wrong, and before you're wrong, you have to do it. Okay, so practice. Go ahead and give it a shot, and then when you're ready to see the results, hit play again. Pause it. All right, let's now take a look at the logarithm examples that you did. So we want to get this logarithm by itself, so we're going to divide both sides by that coefficient of 2. Since 2 divided by 2 gives us the 1 logarithm that we're looking for. So that leaves us with log base 4 of x equaling 3. Now we can use the swirly-do definition. That's not the official definition, by the way, in case you're wondering, where the base of 4 taken to the power of 3 will equal x. So now we can rewrite it without the logarithm. So 4 cubed equals x. 4 cubed is 64, so 64 equals x is our solution. Okay, let's take a look at B. We've got log of x plus 6 minus log of x equals 2. Again, logarithms represent exponents. When do you subtract exponents? When you are dividing like bases. So we're going to change this to 1 logarithm and division, x plus 6 over x, and it still equals 2. So we're still going to use the definition. Just remember, if you do not see a base, It's understood to be the common log or base 10. So if you need to write it there to give yourself a visual, go for it. So 10 to the power of 2 should equal this. So we have 10 squared equals x plus 6 over x. And this is when you start to wonder, am I doing it right? Because it looks a little complicated. But yes, you didn't end up with a linear or a quadratic. You got a rational. But that's okay. Keep going. We're going to clear this fraction by multiplying both sides by the x, by that denominator. So those two x's divide out. That leaves us with a 100x equals x plus 6. And then when you subtract the x from both sides, minus x, and we'll move it up here so we can see it a little bit better. That's going to give us a 99x equals 6. And again, some people even stopped here and went, well, I must have done something wrong, because look, when I divide by that 99, I get this weird answer, even if I simplify it. I get, let's see, 3 goes into both, what, 2 over 33? Well, that can't be right. And then people start erasing everything and start recreating math. Nobody promised that this was going to be pretty. It's algebra. So sometimes you're going to get some answers that aren't as nice as others. That's okay. Trust yourself. Even if this answer was wrong, a lot of teachers do give partial credit. They want to see, did you know to change this subtraction into a division with a single logarithm? Did you know how to use the definition to rewrite it? Did you know how to clear the fraction here with your rational? There are certain pieces that shows where your logic is. So if you got this far and you stopped, your issue isn't the math, it's your self-confidence. Okay? So be sure that you don't give up and rewrite it. At the very least, do it a second time, but don't erase it. That way you can take your homework or your test or your quiz back to your instructor and say, well, I did it twice and here's what I got. Can you show me what I did wrong? And that way you can learn from it. Okay, the very last one, we've got a natural log of 2x, which means you have an understood base of e. Remember, e is a number, not a variable. So you can use the definition, e to the power of 7 should equal 2x. Again, e to the power of 7 equals 2x. So to get the x by itself, you would divide both sides by 2. And so x equals e to the 7th divided by 2, and this is your exact answer. And you can always put it in your calculator and come up with the approximate if your teacher wants that. So how did you do? Well, remember a few things. First of all, we cannot get the variable alone if it's attached to the log or the ln. That's where the definition comes in handy. We need to get the logarithm by itself using the logarithm properties, which again are affiliated with the exponent properties. So think exponents. And we can use the definition to rewrite it without the log or the ln, the log or the natural log portion. Just a review of the definition, log base a of x equals c. If you take that base, take it to the power of c, it should equal your x. So a to the power of c equals x. And honestly, I still write this oftentimes when I'm doing work with students, the swirly do, or if I'm nervous or I'm tired. I'm like, oh yeah, okay, so here's my base, it equals that, it equals that. The more you do that, when you get to a test and you're nervous, your hand will be circling, doing the little swirly do before your brain catches up with it. So go ahead and write it with every problem so you don't forget. But notice this definition only works when you have one log. So don't forget to use your logarithm properties to rewrite it down to one log, then get rid of the log. Okay? So thanks for working. Yeah, thanks for working. Thanks for watching. Thanks for being here. Remember, if you have any questions, you can watch the video again. You can look for other videos. Ask your teacher, ask your tutors, ask your friends, but ask, okay? Don't let your pride keep you from passing. You're not alone. Hopefully, we'll see you soon. Hi. Now we're going to take a look at solving exponential equations. Here's the generic form, a to the x equals b. Remember, your base has to be greater than 0 and it cannot equal 1. What makes an equation exponential? Well, your variable is in the exponent position, hence exponential. So what do I need to know? First of all, how to rewrite bases and exponents, and your logarithm properties. If you're still a little weak on the logarithm properties, be sure and watch the video again. And there's a lot more detailed videos out there. Check your notes, check your teacher, because it will really help you with a lot of the exponential problems as well. Now, some exponential problems are easier than others. We've got here 3 to the 7th equals 3 to the x. Well, I call this kind of the kindergarten way of looking at it. If your bases are the same and both sides are equal, then your exponents must be the same. So if 3 to the 7th equals 3 to what power? Well, that power has to be also 7, because only 3 to the 7th equals 3 to the 7th. If the bases are the same, then the exponents must be the same. What if the bases aren't the same? Well, if you can rewrite them so they are, if possible, then do so. For example, here we've got 8 to the x equals 2 to the 4th. I can rewrite that 8 as 2 cubed. So 2 cubed taken to the power of x, we can multiply the exponents there, and we can set the exponents equal to each other and solve. So 3x equals 4, which means x equals 4/3, or 1 1/3. Now the problem comes when there is no common base. Then we have to use logarithms. Remember, logarithms and exponentials are inverses of each other. When we're solving logarithms, we're able to use the definition, the swirly-do that we talked about in the previous video. If you didn't watch the logarithm video, then the swirly-do means absolutely nothing to you. But it's the definition of the logarithm, swirly-do. So feel free to look at it. But when we have a variable in the exponent position, there's one particular property of the logarithm that we're going to use a great deal. Recall that logarithms represent exponents. So here we have an exponent to an exponent. That's when we multiply. We are allowed to take this exponent of x and move it to the front based on the properties of logarithms. Yay! So notice here, your x is an exponent. You have a variable exponent. Your goal is to get that x out of the exponent. Remember, we're supposed to whittle it down, get rid of our obstacles so we can get x equals a number. Not something to the power of x equals a number, just x equals a number. So when we move it to the front, it's no longer an exponent. And we can deal with it like we've done before to get the x by itself. Multiply, divide, add, subtract, whatever we need to do. So recall this. We love this. Star it, highlight it, whatever you need to do. And let's take a look at an example. We have 3 times 4 to the x equals 21. It's an exponential because your x is in the exponent position. So we want to get this factor here by itself by dividing both sides by the 3. So we get 4 to the x equals 7. Logarithm is what undoes that exponent, that variable exponent. So we're going to take the common log of both sides. And that means we can now move, notice it's on both sides. So now we can move the x to the front. And now we have x times log of 4. To undo multiplication, we divide. Now we're not going to divide just by the log, just that little segment. Remember, the log by itself is meaningless. It has to be attached to something to represent a number. So the log of 4 in its entirety is what we're going to divide both sides by. And we get x equals log of 7 divided by log of 4. We're going to go back and write down the steps. First of all, we get the base and the variable exponent alone. That's when we divided both sides by 3. We take the log of both sides here, or natural log, depending on what your base is. Usually it's the common log, unless we see an e. Now remember, this allows you to move the exponent to the front. Now we've gotten rid of the obstacle of the x being an exponential, being in the exponent position. And we can solve like we normally do just to get x by itself. It's x times log of 4, so we divide to get rid of that log of 4 here. Now, there is a difference between what we call exact answers or approximate answers. Your teacher may want both. They may want just the exact. Some teachers just want the approximate. So this is what we would call an exact answer. It's exact because we didn't use a calculator. We didn't have to round any decimals. We leave it in logarithm form. If you put this in your calculator, log of 4 divided by log of 7, you're going to get a long string of decimals that you'll have to round or truncate. Whenever you round, in other words, we can't write all of them, you're going to want to use the little squigglies instead of the straight equals. This means approximate. And the approximate answer, generally, you have to use your calculator and your result's going to be in decimals. So that's the difference between those two, just whether or not you use your calculator. So, for example, e to the x plus 3 equals 20. We get the e to the x by itself, because remember, it's the variable that we're looking for. We have to get that variable out of the exponent position. What does that? Logarithms. How this one's different, though, look at our base. Our base is e. Remember, we usually use the common log or the natural log. If we see nothing but numbers, common log. If we see an e, natural log. That way we have the same base. So we're going to take the natural log of both sides, and there's two ways of looking at this. First of all, what we did before, we're able to move the x to the front, and then we can divide by natural log of e. But remember, the natural log of e is the number 1, which is handy. That's why we took the natural log instead of the common log. So we can simplify, because the base of the natural log is an understood e. So that gives us the natural log of 17, which the approximate answer is 2.8332. Yay! Now, another way of looking at it is when you look at the base e here, if the base of your log is the same as the base of what you're taking the log of, then that side just equals your exponent. So x equals natural log of 17. Now, honestly, most people forget this little shortcut, but let me show you where the shortcut comes from. Your base e to the power of the natural log of 17 equals e to the x. Yeah, it's the definition of the logarithm, the swirly do. So if we rewrite that, e to the natural log of 17 equals e to the x, your bases are the same, therefore your exponents must be the same. Therefore, x equals natural log of 17, which the approximate answer is 2.83. Yay! So it's the same as what we got before. There's not one method more impressive than the other. They both say basically the same thing. You definitely get the same result. So now I want you to try. Here are 3 different examples. Pause the video when you're ready. If you feel like you need to watch it again before you try them, that's fine. But when you get back to this point, pause the video, try all 3 of them, and it's okay if you're wrong. We're going to go over them and kind of see where you made your errors. Hopefully you won't be, but if so, it's not a big deal. You're going to correct it, and you're going to see where your errors are, and that way you can master it next time. Okay? So go ahead and pause it and hit play when you're ready to watch. Pause it. Hi. So now we're going to take a look at the exponential problems. We can tell it's exponential because our variable is there in the exponent position. So again, remember, we got to whittle it down to x equals a number. So we need to get this exponent out of the exponent position. So let's first of all get this factor here by itself, the e to the x by itself, by multiplying both sides by the reciprocal of the 1/2. In other words, multiply both sides by 2. Kind of squeeze that in there. So that way the 2's reduce, they divide out to 1, and we get e to the x equals 10. Now because we have a base e, we're not going to take the common log of both sides. Some people say, well, we've got a 10 over here, why don't we take the common log? You could. I'm not saying that you would get the wrong answer, but it's kind of the long way around, because we're worried about this variable that's in the exponent position, so we want to undo this. And here the base is e. So that's why we're choosing the natural log. So let's take the natural log of the left, which is e to the x, and the natural log of the right, which is your 10. Now remember, because the understood base of the natural log is e, if your bases are alike, it equals just whatever your exponent is. But you could still also move the x to the front if you want, because the natural log of e is 1. So either way that you look at it, it's still going to be correct. So this reduces to just the exponent, because the base of the natural log and the base of this is the same, equals natural log of 10. Now, this is your exact answer. And if you plug that into your calculator, we will get approximately 2.303. So this is your approximate answer. And you can ask your instructor which one they want, or they may ask for both. So just be prepared. Let's take a look at the next one. We have 2 to the 3x equals 9. We can't get our bases alike, so we're going to take the common log of both sides. So the log of 2 to the 3x equals the log of 9. Okay, again, this allows us to move that to the front. Our goal is to undo our obstacle. Our obstacle is the fact that the variable we're trying to solve for is in the exponent position. So to undo that, we take the log of both sides, and we get 3x log of 2 equals log of 9. Now we want the x by itself. Everything here is being multiplied. 3 times x times log of 2. So we're going to use division to get the x by itself. We're going to go ahead and divide by the 3 and the log of 2 at the same time on both sides. 3 log of 2. So on the left, so those 3's are gone, the logs of 2 are gone, and we get just x equals log of 9 divided by 3 log of 2. This is your exact answer. Okay, I'll write it underneath this time. This is your exact. If you're to put that in your calculator, we would get approximately 1.057. Okay, there's your approximate answer. Now, one thing I want to stress about your calculator, depending on whether you're using a scientific calculator or I just went blank. Oh, graphing calculator. A scientific calculator or graphing calculator will depend kind of how you're putting these in. But even with the graphing calculator, where you put everything in at once, you have to be very careful with your parentheses. If you just put in log of 9 divided by 3 log of 2, you're going to get the wrong answer. The reason is your calculator is using order of operations. So they're going to take the log of 9, they're going to divide it by 3, but they're only going to divide by 3. And then they're going to take that result and multiply it by log of 2. So you have to put in a parentheses here and here to tell your calculator that you are dividing by this entire thing, not just the 3. Okay? So you have to be very careful with that. Whenever you have more than one factor or piece down here in the denominator, be sure you put everything in parentheses when you put it in your calculator. All right. Now in C, same thing. We want to get the x out of the exponent position. We can use a logarithm. Okay, there's nothing wrong with that. But if you notice, I've got this, which I can write as a base 3, the 1/3, and the 27 that I can write as a base 3. So back to kind of the beginning problem before we did logarithms, I can write that 3, or the 1/3, sorry, as 3 to the negative 1 to the x, and that 27 as 3 cubed. So we have 3 to the opposite of x equals 3 cubed, and if your bases are alike and they're set equal, then your exponents must be alike. Therefore, negative x, or opposite of x, equals 3, so x equals a negative 3. So how did you do? Good. Well, let's take a look. A few things to remember. First of all, exponential equations have the variable as the exponent. If we can, we want to rewrite each side with the same base, if possible. Otherwise, we're going to use logarithms to undo that exponential. They're inverses. Well, hopefully that helped. If you still have questions, feel free to watch the video again. Look for other videos online. Ask your teacher, ask your tutor, ask your friends, but be sure and ask. Don't let your pride keep you from passing. Believe me, there's always tons of questions on the logarithm section because there's a lot of different pieces to it. So don't let your pride keep you from passing. You're not alone in this. Thanks again for watching, and we'll see you again soon.